Welcome back, everyone. We'll get started in just a second here. All right, welcome back, everyone. I hope you had a good evening and night last night, and welcome back. It's Friday. It's time to dig in, and today we're going to talk a lot more about Julia's packages and about how you can really begin leveraging Julia to work with lots of data, do a bunch of advanced techniques. I think it's going to be a fun day. As we get started here, we already got a request to, how do I launch Julia from the, without going through VS Code. So let's, whoops, that escape button closed my chat window. I want to open that back up. There we go. So let's dive in. So I have VS Code open here, right? And if I want to launch Julia, instead of, going into this larger, it kind of feels a little heavyweight at times, the integrated development environment. This is something that I do quite regularly, and kind of depending upon your familiarity with systems and how familiar you are with command line prompts and things like that. The way you do this will likely be a little bit different. But we can go in here and let's just go in and wonder what versions of Julia I have installed here. Looks like so I'm on a Macintosh. What you'll see in your computer is going to be different based upon what you're using. I have a bunch of versions of Julia Pro installed. That old thing that I was talking about, we'll have a new version of that probably within a few months that's based on VS Code. But I also have this Julia, it's an older version, it's 1.3, but the same idea will apply. This version of Julia here is what I installed, or what you would have installed from the website. And if you did this through Windows, it'll look similar. If you did it on Linux, there'll also be an app kind of like the same idea. And when I double click it on my Mac, it'll pop up a terminal window. And I've never double clicked this. There's a reason for this. I'll show you why. And it'll open up a terminal window ready to go, and it just gets things set for me to write and type in here. I can make this bigger so you all can see. This is what you would see if you just launch Julia directly, and how you do that. It'll be it'll be different. But this is how it is. You can get a little bit of details about what you're running with the version info command, do all the things that we've been doing, but you don't have access to the editor, right? And so some folks prefer this in this kind of workflow. I actually prefer this quite a bit, and this is how I work with Julia, and the key thing that I do is you'll see that, when I launched this, buried inside the application here. So this is the, applications, Julia 1.3. This is what I double clicked. But tucked away inside, hidden inside it, is the Julia executable, the command line prompt thing that runs. And so if you're familiar with command line, you can actually run this directly. And so, I like to use a different terminal than what is provided by default for the operating system. And I can just paste this in here and get that running. And then, of course, if I'm familiar with this, I can do all sorts of aliasing, things like that. Now, the one thing that's a little tricky for those of you who are on Windows, the default Windows terminal thing here, the interface through which you access the REPL, kind of stinks. It's not very full featured. It's pretty limited. It looks pretty scuzzy. It's not, it's very pixely. It's not, the nice swanky smooth text, and it is a little hard to work with. If I remember right, you can't even select text, which makes it really painful to like copy and paste and do the kinds of things that you want. So a lot of folks on Windows end up installing an additional terminal or lean more heavily on the VS Code REPL. And so the reason I don't do this at the beginning or talk about this is because it is really platform dependent, right? What I do on a Mac is going to look very, very different than what you do on a Windows or Linux machine. And so it can be a little bit tricky. And yeah, so that's the key thing. I mean, I think the main thing here is, lean on VS Code, gain familiarity, and then as you gain familiarity, there's lots of great things that you can learn about how you do this. In fact, with the way that I have this all set up for myself is I have lots of versions of Julia available to me at the command prompt. I've set up my command line so that way I can do development on both Julia and Julia Pro. I build from source. I have them all versioned and everything. And so you can ask, where these things are and what they're doing, and I just have them installed locally. So this is a little bit of inside baseball here, but there's lots of ways that you can get this set up. So that way, if you open a command terminal, you just hit Julia and hit enter, and you get hopefully the latest release or whatever you've installed. All right. I guess the last thing to note here is just you can see that I have, what is that, 12 different versions of Julia installed on my machine, and they all coexist very, very nicely and work just fine. So with that, let's go back to our VS Code environment. I still have this set up in my, in this folder. Just as a reminder, if you've lost this, what you can do is you can go to this Open Recent folder here. Go to the file menu, Open Recent, and the Introduction Training folder should be at top of your list, and do this. So that is how you do this. The way that once you're in here, again, to pull up the REPL, you can go to the command palette and start the REPL, and it'll pop up down here. I guess maybe I'm not understanding your question, David, about how do you get the REPL from Julia? Like if you're, so I guess kind of the way to get the REPL is, right, if you're at a command prompt or something like that, you just type Julia and it'll open the REPL and get things going. If you have a script that you're running, right, you can create a script and run Julia script.jl, something like that. I don't know if you have a script.jl in your home folder, and Julia will just run that script and exit, right? It'll exit and get out. And never open up a REPL. And so is that where you're after a REPL? Is if like you're in the middle of a script that you're running kind of without a REPL, how do you get back to a REPL? We can talk more. Yeah, let's talk more about it during the break. We can play with it. There are ways to do this with the command line. Because a lot of you coming from other languages may be familiar with a more traditional kind of programming language interface where you write a script and then you execute it, right? And you just go back and forth. And every time you make a change to the script, you launch Python again and execute the script again from scratch, right? And kind of the workflow that we use in Julia more frequently is to have a single long-running Julia process that then you incrementally develop on and keep adding that way. So it's a little bit of a different workflow than you may be used to using, but I find it much more productive, and it matches the way Julia works, especially once you start talking about packages, which is where we want to go today. And so if you'll recall yesterday, talked about VS Code, talked about the basics of Julia syntax from arithmetic to arrays to functions, and then some extra data structures. So that's how that works. And the next notebook here is Notebook 5. It's an example on image compression. I'm actually going to skip that because I think it'll be helpful. It uses some packages, and I think it'll be helpful to jump directly into talking about using external packages and getting things going that way. And then we can go back to image compression. It's kind of a fun synthesis of a lot of what we've learned and kind of a nice way of pulling it all together. And then we can talk about plotting, which is, of course, one of the most used packages for data science. One last point on this REPL thing. This is the REPL right here, this Julia prompt. If you see a Julia prompt, you're in the REPL, and that's it. It's doing its thing. This is the Julia REPL. And so, yes, you are. This is on the REPL or in the REPL, you could say, of Julia. And yeah, that's it. If you remember, you can get to a bunch of different modes here. And if you want to get back to Julia, you just hit the delete button. So if you're in the help mode, hit delete and you get back to Julia. So let's pop open the packages notebook here, and I'll close out the file browser, open this up. We'll open this up. This is actually woefully out of date here. We now have, I think this is on the order of 4,400 packages that are registered. And one of the best ways to start digging into the package ecosystem is online. And there's a website that we've developed at Julia Computing called Julia Hub that allows you to, let's see, here we go. That allows you to look at all the packages that are available. You can, see what all is here. Actually, I need to zoom out just a little bit to get all the tags going. And you can see all the packages, the most popular ones, as well as popular tags. You can poke around here. It's a great way to explore the ecosystem. So for example, one of the most popular tags that packages are tagged with is machine learning. So you can click here and see all the packages that are tagged with machine learning. Julia itself is all aboard the hype train and tags a bunch of things that are relevant to the language. But then here are some packages that can actually do machine learning or help you with machine learning. Flux is our toolbox. There's a probabilistic programming system. KNet is another deep learning framework. Lots of things here that you can explore. You can click on them. You can jump out to their documentation. So there's a nice machine learning framework. All these things are here. This is a great way for discovery. You can also just go in and search through all the packages for a particular thing that you're looking for. For example, if you're not sure how to do fast Fourier transforms, you can just search for FFT, and it'll go through the entire documentation ecosystem of the language itself, all 4,400 packages and more, and show you how you can, do fast Fourier transforms. The first hit here is a pretty good one on, what's the FFT function and how do you do it. So I just want to point you to Julia Hub as kind of a great entry space to find packages. But once you've found a package you want to use, how do you actually use it? What do you do, and how does that look? So let's go and see what this is. Oh yes, there's also another service out there that kind of presents the same information slightly differently. It's called Julia Observer, and it's also a great solution here, worth talking about. But yes, there's a really nice way of looking at all of these things. This just kind of categorizes it slightly differently. I think they lean on a different categorization and such. So all great things. This doesn't do documentation search though. This is just like package search. Okay, so how do you do this? How do you get things going? Well, you can do this just by code. The package manager in Julia is called PKG. And the way you bring in packages is with this using statement. So the package manager is itself a package. It's a little meta there, but you can go in with and bring in all of its functionality just by saying, hey, let's use package, use the functionality provided by package. So I can execute that line. That just makes that package's functionality available to me in my current session. And then I can do things like add a package to my current environment. So I can go in and say, hey, let's add the example package. And it goes in, gets things set up. It'll update things, download everything that I need, and hopefully you'll see that you install a version of example. Now, there's some things here that are kind of cool about the way this works, is that it keeps track of all the packages that you're using. Julia does. It knows about what packages there are, and it knows how all of their versions, all their dependencies, and it makes things entirely reproducible within an environment. And so you can see here in the gibberish that's happening, what's getting printed out here is fairly straightforward, right? It's going in, it's updating a registry. I don't think you'll see this line. I've added a extra registry here, but you'll probably just see the general registry, and that's fine. And then, so the registry is kind of the list of all the available packages, what versions they are, where to get their code, and so on and so forth. It figures out what versions are compatible with everything that you've installed so far. And then it adds them to these two files. There's what's called a project and a manifest. And we'll talk about how they work in just a second. But you can see here that we've added example version 0.5.3. And if I go back over here to Julia Hub and just go in to the example package, it is of course listed here. I can go into its documentation and see that it provides two functions that are very simple and silly examples. You can do math or you can say hello. And so if I wanted to call these, how would I do that? Well, remember, the way that I did that here was with using, right? When I wanted to use the package manager, I said using. If I want to use the functions available from example, I just say, hey, using example, and hit enter. It'll compile it, get it ready for me. It's a very small package, so that takes very little time. It'll only do this once per version that you've installed. So once we've done this once, it won't need to do that again. Now I can ask for help, right? Remember, there were two functions here. I could say, hey, what does do math do? And of course, its help is available here. So then I can do math with a given number. And that will add 5 to it. So that is how you can get things set up, how this works. I'm going to close my Julia session now. And there's several ways you can do that. You can, let's see, can I Julia stop? REPL, yeah. So you can use the command pane. Remember, view, show command palette, or the Control-Shift-P, Command-Shift-P, something. And I can stop the REPL. That'll close it out. and I can start it back up again. The reason I'm doing this is I want to show you a different way of importing that package. So I've added that package to my environment. That means that it's here no matter how many times I start and stop. It's always going to be there. There's another way of importing packages that's called import. So remember before I had said using. If instead I had said import example, it does something slightly different because now I don't have access to do math, not do match either, but do math isn't defined here. I've imported the package for me to work with, but I can't do anything about it. And the reason for that is because this is now needs to be qualified. It needs to be, its accesses need to be example.doMath like that. I need to explicitly qualify where this doMath function comes from. So those are the two key ways of working with packages. You can either import them, which just makes the package name itself available for you to work with here. So I can do the exact same thing. I can ask for help. I can use the hello function, right? That works just fine. But I can't use them directly, right? I can't just say hello, Matt. It'll say I've not defined hello in this namespace. It's defined in the example namespace, but not in my local one. If I now say using example, now that brings in all of the exported names, all the defined names from the example package to my local namespace. So that way I can work with them directly. And now what I had written will actually work, right? Because I'm using it. For those of you coming from Python, this is exactly like from example import star. It's the exact same concept. And the only difference is that in Julia, we're not as strict about that being a verboten thing to do. So Python folks really don't like this. There's some good reasons for it, right? Because if you're in a deep nested code base and you want to know where this hello function came from, it might be from one of many packages, right? And you don't know which package it came from. And so it can be a little bit tricky there. This is where an integrated development environment, though, makes your life a whole lot easier because if I just type hello in my VS Code environment here, it is defined and it knows that this is here. Let's see, I think it should be defined. And if I hover, oh, interesting. I would expect this to pop up the interactive help for it. I guess it's not doing that. I wonder why that's not working. Maybe I need to explicitly say using. It might be I think it needs to be, I need to explicitly say using example here, and then it'll know that that's there. Maybe? No, it's still not popping up. Interesting. I'm not sure. That has worked for me in the past. I'm not sure why it's not popping up here now. But often you can go in here and see, where's this defined? Although, again, it's not popping up there. Interesting. I'm not sure why that's not working. Yeah, that's all right, though. So this is the kind of thing that, it becomes difficult to reason about, right, if you have lots of packages. And so there are times where it's nice to explicitly mark that. And so instead of saying using example, you do import example and then example.hello. And it seems like in Julia 1.6 or somewhere soon, there's rumblings that we may be able to import example as an alias, kind of like what you can do in Python to reduce the amount of boilerplate, right? To reduce the length of code. Right now, if you wanted to do the Pythonic sort of thing, you could say const x equals example like that. And then you could just refer to this as example like this. And that'd be the same idea. So there's talk of a syntax thing here. What I've done here is a little bit different. I've used the const keyword. That just says, hey, this is never going to change. And if I tried to change it, it'll give me an error. It'll say, hey, that was a constant. I can't redefine that. And it allows Julia to do some extra optimizations. So that's all const does there. It's just a little annotation on the assignment that comes after it. And I've kept using capital letters here. There's a very, very strong convention in Julia that modules and packages are capitalized, and with capital case, all the things smushed together. So if this were a multiple word package, I'd say import example package like this or something like that, right? This is the style of doing this. That's very common. And the other convention that's actually really nice for searching and such is that we name our packages with a .jl suffix. And so the technical name, the way this package looks on GitHub and the way that you can search for it is just with a .jl. So it's not a Julia script, right? It's an entire package. It's a folder with lots of things inside it. This is the source code for the example package, again, hosted on GitHub. And you can see that the name of the repository here isn't just example, it's example.jl. And that's nice for several reasons. One, it very clearly states, hey, this is a Julia package. The other thing that's nice about it is that it adds a little bit of search fodder to every single page. Everyone that talks about a Julia package, there's probably a JL on the end of it. Julia as a word itself isn't the most searchable word, but JL is a beautifully searchable word. And so often if you're searching for a technique or want to know something about some code, you can just search, remember I searched for FFTs. If I do FFT with a space and then the JL package suffix, I can go in and see, oh, here are some packages that implement fast Fourier transforms. And they are hosted on GitHub, named FFTW or FFT something.jl. Here's a sparse FFT.jl. All these things are really nicely, all the results that I'm seeing here are Julia results for the first, this one's not Julia centric. But everything up until this result here was a Julia result. So that's a great way of searching for things. All right, so that is, the basics of package management. There's a little bit more depth here that I want to go into that's not written down in this notebook that we can talk about. So let's look at what our status is. So remember, we can do import pkg and then ask for pkg.status like this, right? It's a function inside the package manager package itself that asks for status, and it tells me all the packages that I've added. And what you'll see will look something different than me. You might just see a single line that only says example here. And that's fine. These other tools that I have here are packages that I've added to my global Julia environment, the default environment that Julia starts up with, that are helpful for me in my everyday development workflow. So essentially all of these packages, with the exception of example, are packages that I probably want to use with as development tools, but not necessarily for the actual code of a project. And all of these are going to be available in every Julia session that I start. Now, what makes Julia's package manager extraordinarily powerful and one of the unique features is that it builds in this idea of an environment. So you can kind of get that idea just by where this environment is this default environment is right now. So you can see that on my computer, it's tucked in this hidden Julia folder in my home directory in an environments folder that's very evocatively named in its current version, right? So this is versions. So if I update to Julia 1.6, when that comes out, I'll have separate packages because the dependencies and the compatibilities might be slightly different. So that kind of helps separate out exactly what's going on. But what's really nice about this is that I can set up local environments that are specific to the code that I'm going to be using. And so I very intentionally didn't do that for this course, even though it would be helpful for this course, because I want to teach you all how to set up a local environment for this course and get you all going with the local environment. And so the way to do that is to what's called activate our current directory. And I want to activate the environment of our current directory to use as our environment for this course. And so I'll use that package manager and do pkg.activate. And it's a function. You can ask for help on it. It'll tell you a lot about what this does and how it works. And it activates an environment. So those are just words that I've already said. Probably isn't that helpful. It's without understanding more about what activate means and what the environment means. But what it means is that it's going to set up a local project, essentially, that has a different set of packages potentially than other environments in my that I'm working on. So let's do that. Let's pkg.activate this current directory, and a nice little shortcut to your current directory is just a period. This is a little shortcut on all the major systems, Windows, Mac, and Linux. The period string, or the string that just contains a period, refers to the current working directory. And VS Code, when it launches, it automatically sets up your current working directory to the folder that you're working on. So it's a nice little way of thinking about that. You can actually see that with Julia. I think it's CWD, or is it? Well, I can't remember how to get it. But yeah, you can. Oh yeah, it's PWD, print working directory. Will tell me what my current working directory is, but I can also refer to that just with the period. So if I activate pkg.activate this period directory here like this, it says, hey, I've activated a new environment. I've now have, instead of the environment that I was using, right? I now have a local environment at the path to where I have, and it adds what's called a project file. And that project file is what tracks my dependencies. So that is how you can activate environments and get things going. Now let's ask for the status again, right? pkg.status, and all of a sudden it's empty. There's no dependencies here. There's nothing that is set up to work with, that I have working here. So again, I would want to add that example, right? pkg.add example to make it available to me to work with. And it'll go out and add example. Now, instead of updating my global environment, it's just changing my local environment. It's only changing that local environment and getting that going. And so this is how you can start working with this, how you can start playing with it. It's a great way of tracking versions on a per project basis. So with Python, if you come from that ecosystem, this is very much like a virtual environment, only it's tracked right next to your code. And it's not external to your code, it's a part of your code. And in fact, many Julia projects that you get will ship alongside them a project and manifest, so that way you can activate them and get the exact dependencies that they were using. Let's add another package here. Before that, I want to talk just a little bit about how I've been doing this, right? I've been using the package manager very explicitly with all these PKG dots, right? I've been reaching into the PKG ecosystem and adding it and getting things going. So that is how you can do this. You can also do this through, remember that special package manager REPL mode, where if you hit a close bracket, and you set this up with a close bracket, it'll pop up and show me a package prompt. And now, unlike before, I don't know if you remember before, this said v1.5. It was because I was in my global package environment for Julia 1.5. Now I've changed my package environment to this local package environment, and you can have this. And yes, pretty much all of the commands that are available at this prompt are also available programmatically like this. If you're running Julia, in a script, or you want to programmatically interface with the PKG package, you would use these sorts of things. But if you're doing it interactively, like I am here, it's so much nicer to work with this, because it allows you to kind of avoid a lot of syntax quirks, right? So when I did this, I needed to do pkg.add. It's a function, so I need parentheses here, right? I call functions with the parentheses, and I want to pass in the name of a package. Well, names are strings, and so I need string quotes here. And so there's a little bit of line noise in doing that. The package manager makes this a little bit easier. So one of the packages we'll use in our next lecture is the images package, and that's a bigger package, right? And you can add that just like you did before. But now, because I'm in the special command prompt here, all I need to do is say add with a space and then images. And this is kind of like a special command prompt for the package manager. So no longer do I need to have parentheses, quotes, anything like that. It's much more straightforward. I'm essentially talking directly to the package manager this way, and it gets things, makes life easier for a programmer. That's what we love doing as programmers, right? Making our lives easier. This is one of those such tools. So this is how you can do this. Now, images packages is cool and interesting because it's a much bigger package. So you can see that it installs the images package itself here, right? Package, version, some version number. But it also installs a whole slew of other packages. Now, these are dependencies of the images package itself. I didn't ask for them, right? I didn't ask for padded views or any of these other things. These are kind of the core infrastructure of what's supporting the images package itself. And then you can see what happens. And now there's a difference between what's getting stored in our project and what's getting stored in our manifest, right? In our project, we have all of, we've only added images to our project. So our project just knows that we've added images as a top level dependency. What's cool is that the manifest then tracks all of these other second, third, fourth, fifth order dependencies, all of the things that we need in order to use the images environment. So I can ask, again, for the status, right? I've added example to this project here, and I've added images to my project. Both of these are ready for me to use and work with locally, and I can get them going. Let's see here. But then Julia also needs to know about all of their dependencies, right? And so we track not just our top level dependencies, but also all of the second, third, fourth order dependencies. And we separate those things out into two files, a project and a manifest. And I can actually open them. They're human readable, or at least somewhat human readable. So the project manifest it's what's called a TOML file. It's just like a simple markup language that allows you to do it. And you can see here, we've just added example and images, and these gibberish that follows them are kind of Julia's unique identifier for these two packages. And so those are the two dependencies, two direct dependencies of our environment. The manifest is where things get interesting and cool. And if you open up the manifest, you should never edit this or look at, worry about this file in almost any cases, but I'm opening it just to show you what it is. You can see it starts off with a comment that says, hey, this file is machine generated. You don't need to edit it by hand or even worry about it. But here are all of our second, third, fourth, fifth order dependencies, their exact versions, and even their exact hashes, or kind of a content representation of the exact code that's being loaded. And so between these two things, the project and the manifest, we have perfect reproducibility between different computers. So as long as you have the project and the manifest, you can do that. So when you added images, right, you added all of these extra all of these extra things. So could you potentially say, hey, I don't need range arrays? Well, no, you still need range arrays, right? Images as some part of its code will use this package apparently. And so it's not really possible to strip them out. What you could potentially do, because all of these packages are written in Julia itself, if you're really interested in like stripping out your dependencies, getting things as minimal as possible, you could look at how images is defined and maybe just pull out the small chunks of code that you need. So instead of pulling in the giant, the overarching umbrella package, maybe it would be just as fine to go in here and see, oh yes, I really only need, some image morphology tools and just grab this portion of it, or, some small portions of it, like maybe I just need some distances metrics between two images or something like that. So that's how that goes. Yeah, a really good question from Andre asking, how do you inspect? So when I just am in my package manager mode here, I can ask for status, right? And it just asks for what my project. I can do the same thing, status, with a -M. M stands for manifest here, and it's kind of like a command line flag for a command line utility. And that tells me all of my manifest files. So you can see the status looks at my project, the manifest version of my status looks at the manifest and tells me the versions. It's a compact representation of that manifest file itself. Let's see, how are we doing? Oh, we're in good shape here. So another package that we'll be using and be working with is the plots package. So let's add that to our local environment here as well. Again, it's adding a bunch of things in addition to plots, all the things that it uses to do its stuff, and gets them all installed, all ready to go for us. So let's add that. Let's also add in, so one of the questions a little bit earlier in the day was about how do you expose a Julia computation as a endpoint or an API. And often when people talk about API these days, they're talking about web-hosted APIs. And so let's also add in HTTP, because eventually we'll talk about how to do this. We can go over that. There's a really nice little minimal example there that'll be fun to go over with folks if they're interested in web APIs and such. So that is that, oh yeah, and FFTW is indeed that fast FOIA transform. So when it builds it, there is a step that is available to packages that allows you to build a package. That is, maybe download third-party dependencies, or in some cases, it'll actually compile a third-party dependency and get things up and running. So FFTW is the fastest FOIA transform in the West, is the name of the package. And it's actually written in not Julia. The lead developer of that package has become a huge Julia user. He's an MIT prof and an awesome guy. He's actually re-implemented a lot of it in Julia, but we're still leaning on the C code that he initially wrote. And so it'll download that and link to it. And so that's what the build step does. And if I guess I've already built those on my computer through other projects. And so that's why they're not showing up for me, is because they're already built for my side of things. So that's what building does there. Let's add just a few more dependencies here. Let's add in, we're going to also talk about data frames today. I know that's something that folks want to talk about and use. So we'll just kind of do all of our work, our package management stuff up front here. And there's a good reason for me to do this. I'm also going to use CSV, and you can do multiple packages at the same time. So data frames and CSV, let's add those guys. And that should pretty much do it. Let me just double check what we're going to run over in our next session here. So the image compression example, yep. All right, I think we're pretty good. Nice. Okay. Yeah, that'll be fun. Okay, let's also just add this one package, the ImageMagick package, and get that going. So here you can see this is kind of the new way of building is what's called downloading artifacts, where instead of relying on my computer to build third-party artifacts, we just have a build bot or a machine that builds them for me. So then I just need to download them. And they're called artifacts. And that's the newer way of doing building. And so that's more frequently what you'll see is downloading of artifacts. So just to recap what I've added here, we can just paste all of these guys in so that way you can make sure that you are in the same shape as I am here. Oops. So these are the things that I've added. I'll put them in the chat just so that way folks are aware of what's going on there. So that is kind of how you can manage things. You can see that if you try to add something you've already added, it'll say, oh, hey, I didn't need to change anything. And of course, you can remove dependencies too, right? So I could say, you know what, I'm done with the example package. I can just remove it. RM is a common shorthand for remove, and that'll do the same thing and remove it from our project. Okay, let's see. Is there anything else in this? Oops, I want to go back to my packages. So yeah, we talked about project, we talked about manifest, we talked about environments. And then the last thing that Julia packages kind of enable you is you can, of course, build your own package. And this is, there's a template that you can get set up and build your own package. This would be how you would, build out a package of your own that you could define and get going. So that's how that works. And yes, if you remove something that doesn't, every time you remove one of your top level dependencies, it will automatically go through and remove any second and third order dependencies and such. It doesn't actually remove them from your computer. It just removes them from what's required. I think if you want to remove what's no longer being used by any projects anywhere, you can do what's called garbage collecting, or a GC. And that will go through and figure out, what all is still in use, what all is not in use. And you can, see like, hey, these are all my active projects. I have a lot of active projects, a lot of manifests that are in use, and a lot of artifacts and things, and it didn't end up deleting anything. But if at some point, I remove these things, then the package manager could go in and see, oh yes, I'm no longer using this, and clear up the space for things like, the things that are on my computer. The other thing to note here is that, this is entirely declarative, right? So, in my local directory now, in addition to all of my Julia files, I have my manifest and my project file here, right? And this is entirely declarative. It declares exactly what packages need to be installed. So that means that I can theoretically even just completely delete my hidden Julia folder and re-instantiate my project, rebuild it, and it'll get back exactly to the state that I was before. Any other questions here? Yeah, so to download all the dependencies from a project, if you were to activate a project, so we activate this project, you just type instantiate, and that will get all the it kind of essentially says, hey, this project and manifest, let's instantiate them, let's download all the packages, let's make sure they're all installed and ready to use. So instantiate is the verb that we use there. The last thing that I want to tell you all about is one of the perhaps most important ones, and I'm doing it last because it'll take a few minutes here. We've added a lot of packages, right? We've added some pretty heavyweight packages, in fact. Plots is a pretty heavyweight package. Images is a pretty heavyweight package. They both define a lot of Julia code and use a lot of dependencies, right? And so we've oh yeah, I should say, so I've been using the verbose status. There's some shorthand commands here too. So I can just do st to do shorthand status because we're lazy. So I can do the same thing. So status-m or st-m. So these are all the packages that I've installed, right? Lots and lots and lots and lots of packages. I want to compile them. I want to get them ready for us to use so that way we don't have to wait for them to precompile. And this is a step that gets saved between Julia sessions. And so in order to expedite the remainder of our class, that's why I wanted to add all the packages we're going to use here. To expedite the remainder of our class, we're going to precompile all of these packages. And as you might expect, if I'm using the verb precompile, that's the way I tell the package manager to precompile all of the dependencies. And it'll go through and precompile my entire project for me. And this will probably take, well, I don't know, we'll see. I would guess it's gonna take about 3 to 5 minutes. Hopefully it's less than the 10 minutes that are breaks going to be here. But this is a point on which we've been doing a lot of development, in fact, and Julia 1.5 is significantly faster at compiling all of its dependencies than previous versions of Julia, and the master version of Julia is even faster. And one of the most exciting new features of the upcoming release, Julia 1.6, is that this will happen automatically multi-threaded in the background as you update your manifests and such. So that's how you can do it. If you want to add packages as a string, you can use that pkg.add API that I initially showed and the way that that this goes. So yeah, this precompiling right now is single threaded, but it's becoming multi-threaded in the future. With that, let's take our first 10-minute break while our computers are doing our work for us. We can jump over here and grab our 10-minute timer. And we will come back 2 minutes past the top of the hour here. I'll see you all then. So.
Hello?
Yes.
I'm sorry, I got distracted. I noticed that you were pre-compiling something. Is that something that we have to be doing now?
Yeah, it's helpful.
What are you pre-compiling, just to know?
It is, yeah, we can go back to, let me do the 2 commands that I had folks run were this one and then precompile like that. So they're package manager commands like this.
Also, I did the add. I did the add of all of those packages, and then I hit just precompile.
Yep, and then yeah, you just in package manager mode, you just type precompile, hit enter, and it'll do it. Oh look, I'm already done.
Why do I want to do that? I thought that by adding it, it was already brought the packages and all that, right?
Right, so it downloads the Julia code.
Oh, but it doesn't compile them. It's just the source code.
Exactly.
I see. So, oh, okay. And that's even the artifacts or not? I thought that the artifacts, I understood that was kind of a pre-compiled packages, right?
Right. So artifacts are from other languages that are compiled. The Julia code itself isn't compiled. And
Oh, I understand. So
this
is
step
there,
will just save us, between 30 seconds and a minute in each subsequent.
so I'm coming from Python, right? From the
Yeah.
Python world. And so most of the time, in general speaking, they already have pre-compiled, let's call it
Yeah.
like that. They're not actually, because this is like that, like this one is, it runs in a bytecode machine, right? So what are actually what's doing it? Oh, because this one is a compiled language that can run
Yes,
in an interactive way, but it can compile to make it faster.
exactly.
Okie dokie.
Yeah, we'll talk a little bit more about the execution model of Julia later today. But yeah, the key thing here is just so that way we're not waiting 30 seconds to a minute at the beginning of next class. That's the only reason I did this now.
Okay, I'm going to do that the same. Thank
Great.
you.
Yeah, of course.
I have a last question. I don't know if you're going to talk about that. So, for example, I have a Mac, as I noticed you had too, and this has multi-cores, right? Does Julia support, does the one problem that Python has is that it is single-threaded, right? It runs in a single thread. Does the bytecode interpreter runs in a single thread, or is multi-green, whatever all the words, fancy words they use for multi-threading?
It is really multi-threading. There's a threading built in. We can talk a little bit about that. That's a key subject of next week's class, if you're going to be joining us then.
Yes.
Is multi-threading, and we'll talk a lot about it then. But yes, you can actually use, so I have 6 cores on my Mac.
So like naturally, I can assign cores and I can run process in parallel without having, or I mean, everything can be used, or does it has to be like programmed to use, like parallelization and all that?
It's a bit of a mix of both.
Okay. Okay. Thank you.
Hey, Matt.
Yes, I see that. You're having trouble installing data frames?
Yeah, I don't know whether it's a syntax error or just what, but I'm on a Windows environment. And I have want to type in pkg.add as I've indicated.
Yeah.
It could not be resolved error.
Could you paste the entire error into the chat, like the super long description of what the resolver was trying to do? It just means that you have an incompatible package that got installed alongside.
Well, if I can figure out a way to copy it.
The other thing you could try just doing is doing a pkg.update, and that sometimes can resolve those errors.
Well, let's try that. Generic function with 7 methods.
To call it with 2 parentheses, open parentheses, close parentheses.
Okay. Wait a minute. Do what now? Oh, I see. Okay. It's updating the registry.
Yeah.
Question, meanwhile, data frames.
Yeah.
Is that all in caps?
No, it's, I see what your problem is. You are absolutely right. The issue was you have a lowercase f. It's capital D, capital F.
Okay.
I didn't notice that at first. That's going to be the error there. Or that's the
Okay. And what about manifest? Same thing, capital M.
Yeah, but you should need to be typing that.
CSV is all in caps.
Yes, CSV.
Plots, I think I've got it installed.
Yeah. Okay. then you're in good shape.
All right,
Nice.
well, let's see what happens. I'm finding that each time I have to go in and do pkg.add and then put things in.
That's a fine way to do it. It's just a little bit easier if you use the square bracket at the beginning of a REPL prompt. That'll change it into that PKG mode that I was showing over here, right? Where you type this, if I just type that square bracket at the beginning of my line, it gets into this PKG mode. And then I can add data frames directly like this.
I'll try that.
But yeah, I think what you were seeing was you're typing it with a lowercase f, and so that's why it wasn't able to be resolved. Because case matters.
Could not determine command. Interesting. Maybe I should have put it in parentheses.
I don't think you should need print. It should just look exactly, you know, I would make sure that it looks exactly what's on my screen here.
Well, so far so good. Data frames are getting in. Yep. All right. Couple more to go.
Great.
Okay. It's interesting. On an old, oops. What happened there? Manifest not found.
Don't know that error off the top of my head.
The following package names could not be resolved. Manifest not found in project manifest or registry.
What package name are you trying there?
Manifest.
Oh, you don't need to install that. That's
okay.
Yeah, that's just the name of the file itself that has this. You don't need to install that. That automatically gets generated by Julia, this file. So I think you're in good shape then. It sounds like you
Well, reasonably. I've got CSV to go.
Okay, great. Welcome back, everyone. We were just helping some folks debug installing all their packages and getting things ready for the rest of the day today. There's a question about Jupyter Notebooks. Yes, Jupyter Notebooks are fully supported, as are, so Jupyter Notebooks, the name Jupyter comes from Julia, Python, and R. That's why it's spelled with a Y instead of an I, as you'd expect the planet to be spelled. So Julia, Python, and R, they were kind of the first languages that that Jupyter Notebooks were pointed towards. And so yes, it's a first-class citizen there. There's if you go, so again, if you want to look at this, right, the easiest way is on packages here. I wonder if I just search Jupyter. Yeah, sure enough. So if you just search on the packages for Jupyter, you'll see iJulia is our Jupyter Notebook plugin. and you can click on its documentation and it'll tell you how to install it and get it running and such. I don't think I'll cover that today, but it's a great way of doing interactive kind of exploration. And yes, there's a new thing. So Jupyter comes from the Python ecosystem and was generalized to work with lots of languages. We have a new thing now called Pluto that is Julia native and is a little bit different way of working, but the same sort of architecture where you're working in a browser window, interactive code, and it's completely reactive, which means that changes in code in one cell can affect other cells. It ends up behaving and feeling a lot more like an Excel spreadsheet, which is kind of funny. But that's a programming mental model that we all have and understand. When you change one cell in an Excel spreadsheet, everything else, all your calculations automatically get recomputed and recalculated. Same thing is true of Pluto. So that's another fun one. Again, just type in the planet name here and you end up with the project itself. Okay, so now for a little bit of a fun example, we've kind of now covered the basics of getting things up and running and working with them. Let's go over to our image compression exercise. And we're going to use two packages here. We've already done these pkg.add steps, right? We've already added these packages as we've needed. So that means that we can just use them. And I'll execute that. That'll pull them into my namespace and get them ready for use. It'll take just a second there. There we go. And we have this set up to load an image of a banana. I actually find this to be more fun and more interesting. This path isn't going to work on all of your computers because I didn't bundle this data set in. And I think it'll be more interesting to just download an image directly from the internet or get that. Yeah, let's just download some image and play with it locally. So I'm going to go to images.google.com. And let's pull up an image of William Kahan. William Kahan is kind of a titan of industry, of computer science and of numerical programming. I can go click here. Let's grab this image, copy image address. There we go. And I'm just going to download it. Download. So I'll type this here. Actually, let's do, yeah, I guess we can do that. Okay. So this will, by default, I'll copy and paste it in here because this isn't something that's written in our notebook. This is going to download this image to a temporary folder. You can see that it got saved in some gibberish path. That's just fine. It'll get cleared up when my computer restarts. It's kind of nice to not need to worry about where it goes or what's happening. Just get stored in a path. And the thing, so download is a function that's built into Julia. It's kind of a handy one that allows you to do exactly what it says on the tin. And it returns, or it gives you back a string, right? And we've seen these guys before, and it's just a path. So I now have in images, right? I can, so actually maybe let's call it path instead. Oh, that can be confusing, probably. Let's do that, sorry. So this gives me my path, right? And then let's say my image is asking, the images package gives me this load functionality where I can load an image at a given path. And that will give me my image, and it shows up directly into a tab here when I load it, which is kind of cool, right? This is the image that I had seen on the website, right? If I go over to the website, there it is. I've downloaded it, loaded it with the images package, And instead of printing out something here, right, it didn't print anything out at the REPL. Instead of doing that, it popped up a plots pane and kind of essentially plotted it for me, which is interesting. So what is this image thing, right? I've saved it, I've assigned this name. I've said, hey, let's use this name for this image. And when I tried to display it, it pops up in my plot, which is interesting. So again, the code here is just to say image, let's load this path. And it's asking, you can see what this load function is just by asking for help on it, right? And sure enough, it tells me what it does. It loads the contents of a file. And it automatically figures out how to do so, right? It figures out based upon what the file name is, things like that. You can be a little bit more explicit. There's lots of advanced options there. But this is, what Images does for us and gives us the capability of looking at it. So what is this thing? Well, one of the tools that we looked at, or one of the functions we looked at, was type of, right? You can ask, what is the type of an image? And it's an array, which is kind of interesting, right? That it doesn't display like an array. We've worked with a lot of arrays. And in fact, it's a two-dimensional array. We know that from yesterday, we saw array of 2. So it's a matrix, right? This image is a matrix. The interesting thing here is that it has this funny element type. So yesterday, the element types that we saw were things like float 64s or integers. In this case, we have an array whose elements are this special RGB type. That should be kind of evocative of what it's doing, right? RGB, that sure sounds like red, green, blue, which are the 3 primary colors of light and how computers interpret images. So this is representing a matrix of pixels, which is a perfect representation for a picture, right? It's an array of pixels with colors in each one. So since it's an array, we can do things like, well, let's grab out the first element, right? We can, well, first let's see, what's its size? You can ask Julia, what is the size? So it's 282 rows by 400 columns. That makes sense. It's not square, it's rectangular, it's wider than it is tall. We can go in here and ask, hey, what's that first pixel? And now we spit out something and again pop up a plot pane here. And in the plot pane this time, instead of a whole image, we get a paint swatch. And the first pixel is kind of this muddy gray. Yeah, interesting. So Vish is having an error. I wonder if others are seeing this. What operating system are you on, Vish and Andre? You're both on Macs. Have you, I think maybe I forgot to include ImageMagick. If you haven't, it might be good to pkg.add. I think ImageMagick is going to be, oh, don't smart quote me, is going to be the, oh man, I changed those into smart quotes. Sorry, let me change that. I wish I could, can I edit that? No, I can't. Oh, you do have ImageMagick. All right, it sounds like, so did you, yeah, you got the path. That sure looks like the right thing. So one of the things that, when you look at the load, it tells you exactly what format you can add. And so the format of this picture is a JPEG. So we can try explicitly, let's see if I can do that. So let me try that. Load file and explicitly say it's a format JPEG path. Using, it's annoying. Let me see here. So essentially what's happening is for some reason, you're not you're not explicitly saving this. Okay. So when you used an SVG, that did work? Both didn't work. Okay, well, I wouldn't expect an SVG to work. SVGs are kind of funny file formats. And so that is definitely not going to work. They don't load as images in the way that I'm wanting to work with them. It's just a file format thing there. We do have support. Images supports most of the formats you'd expect, but SVGs are still a little bit of a funny one. So that definitely won't work. And it looks like that's what you're seeing with the, so you can download the files just fine, but the trouble is loading them as an image. SVGs are kind of like a declarative graphic kind of thing. So that's why that's not working. Anyone else having trouble loading this JPEG and getting the picture of Bill Kahan to pop up in your plots pane? I would just, let me just.
Yep, I am.
Oh yeah, you're
Dave, yeah.
also having trouble. I think what might work better, so the load function tries to automatically detect things based on either the file name or the bytes in the file. It's like tries to automatically thing. And so as you can see, when I downloaded it, it kind of clobbered the file name. It doesn't know that it's a .jpeg anymore. So let's try changing that for you all. I'll go in here and download. See what is the help on download. I can never remember which order things go. So so the first, when you ask for help, the first parameter here is the URL. That's what we want. And then there's an optional second parameter. When in our documentation, we use square brackets as an optional argument. It's kind of a funny notation because elsewhere in Julia, remember this would create an array. We're not creating an array here. This is just saying, hey, this is an optional argument. And so instead of downloading him to a random file, let's just name it kahan.jpg like this, and call it my path like that. So this is what, let's try having you all do this instead, those of you who are having trouble. So I'm going to download that same URL to a local file named kahan.jpg, and then image equals load that path. And that should do the same thing, and hopefully that'll work. Nice. When have you got it working? Yeah, I guess maybe the magic bytes. I wonder why that worked for me and not you. That's interesting. Maybe we ended up with different versions. That's one of the challenges. But when I like incrementally getting you all to just set up your own environments, because that's something that you'll all do in a regular basis in your Julia programming career. But that, it has the downside of the fact that we can end up with different versions of packages. Oh yeah, you could also download it manually and load it manually instead of using Julia to load it. That's another way of doing this. So Vish, is that working for you now?
Not yet. I get the same.
Oh, your path PNG there is in quotes. You want to pass it as a variable, not as a string.
Yeah, no, I got the same thing. I did correct that earlier. Yeah.
Okay.
So yeah.
See, I think.
A suggestion to Vish: if you copy from the group, from the Zoom group chat and paste that in, it seems to work. It worked for me at least.
Yeah. So yeah, Vish is trying to load a ping, and I thought that should work. That's interesting that it's not loading a ping file for me either. It's essentially saying that it's, you know, not finding the format or not getting the format correctly. And it might be, oh, I think it's because this actually isn't a ping file. So one of the tricky things about downloading things off of the internet is that sometimes so the URL that you entered there isn't actually a ping. What you want to do is you want to click on the image and copy the image address. And then that's going to be a slightly different. So even though that, that URL ended with a .ping, it actually wasn't a ping file. And there we go, that works. So yeah, it's just this weird thing with, I don't know why a bunch of internet servers are doing this these days, but you can see here that this path or this URL in my file, in my browser here, it shows me that it ends with a .ping here, and it kind of looks like it should be a ping, but actually this URL is to a whole website that has everything, and so you need to right-click on an image and copy the image address in order to get it. That's the challenge there. And one of you is still having trouble with load not being defined. That's simply because you've not used images. So using images should get you to where you need to go. That's the package that brings in the load functionality. All right, this is great. Thank you all for stopping me and getting things going. So let's go back to our image of Bill here. And, you know, remember it's an array, we can index into it. We can go a little bit towards the middle of the array. So let's say go 150 rows down, 200 rows in. There's a deep red. You can kind of explore around the image and you get these paint swatches from different places. Maybe that's, you know, part of his cheek or something, a little bit of a, I don't know where I am in the image, 150, maybe 100 rows down. There you go, that looks more like his face maybe. You get these paint swatches coming out. And a nice little feature of VS Code here is that in this plots pane, this plots tab that's popped up here, I can click these back and forward buttons to see all the things that I've generated. So you can see that I have 10 plots total that I've generated, or 10 outputs might be a better word for this. It's, you know, these aren't plots themselves, but they use the same infrastructure as plotting does, which we'll see later on. You can go back and forward in what we've done, what we've seen. So you can see all the different things that I've pulled up and go through here. You can also use this trash can to delete a given plot, and it'll clear my history for me. So you can play with things that way. So just like, you know, before, right, with arrays, you can do slicing of an array, right? So we could potentially grab, say, the first 100 pixels and the first 100, or the first 100 rows and the first 100 columns to give me a little square. It gives me, you know, the top left quadrant of this. To get the dimensions, or this, you can ask for the size of the image, and that gives me the number of rows, the number of columns. You can also ask, you know, what are the total number of dimensions? How many dimensions does this image have? You can say, hey, what are the number of dimensions of this image? There are a lot of these kind of little helper functions. You could also ask what the length of the image is. That tells me, you know, the total number of pixels. All of these things are just kind of, these are kind of standard things that you'll see throughout lots of Julia code, and good things to keep on your fingertips. Size and length particularly. So how do I actually see what these things are, right? Remember that I can look at image of, you know, say 100, 100 and find, oh, that's really dark. Let's go to 200 maybe. There we go. find this paint swatch. What is this element that I'm pulling out of my image, right? I'm getting a single element, the pixel, 100 rows down, 200 columns across. What is it? Well, I can ask for its type. And that's one of these RGB things, right? Remember, the type of our array itself is an array of RGB things. The type of a single pixel is going to be one of these RGB things. And so that's going to be the, how we talk about them. What are these RGB things? Well, there's a kind of a internals function that's, you don't really need to reach for that frequently. Actually, I wonder, can I ask for, let's call this my pixel. I can ask for help on a pixel and it'll tell me a little bit about this, right? It says that, hey, there is no documentation found, right? I just defined this pixel thing. I haven't attached any documentation for it, but I'll tell you a little bit about the type. And pixel is a name that is in my current namespace that's of type RGB with some fancy parameters and curly braces here. And Julia's like, well, I don't know what to do. I didn't find any explicit documentation here for this particular object, but why don't I just tell you a little bit about its type instead? And so this is the structure of my type. And you can see that there are 3 fields of my type. There's a red field, a green field, and a blue field, or an RGB field, which sure sounds suggestive. And knowing a little bit about the images package, I know that there's red, green, and blue functions. So I can ask for the red value of my pixel. And that gives me 0.89 some gibberish. I can ask for the blue value of my pixel, and that gives me 0.56 and some gibberish. And I can ask for the green value of my pixel, and that gives me 0.61. And so here you can see this is the, hopefully you can kind of start imagining what's happening here or what's going on. These are the relative intensities of red, blue, and green of our image. And if I say, okay, well, let's look at this RGB thing. If I, ask for help of an RGB, it tells me a little bit more, right? So RGB is this type, and it is the standard red, green, blue color space. And they range from 0 to 1. So that's how this is working, right? And I can explicitly generate this pixel. So I have an RGB of 0.89, 0.65, and 0.57, like this. I can manually define this, and I get a color swatch that's going to be slightly different, right? I didn't exactly represent those things, but it's almost exactly the same as what I had before. So this is a pixel. And a pixel in computers and the way things work, they're just numbers, right? They are just numbers, and that's all it is. The funny thing that's happening here, this N0F8 that's appearing after our numbers, that's just Julia being efficient about how it's representing these numbers. It's matching the hardware representation of how images work. If I were to explicitly dump out the internal representation of this pixel, so dump is another function that you'll sometimes see, you can see that there's an R intensity with a unsigned integer. Remember these things that are in hexadecimal, and I said they're sometimes used for colors. This is precisely how they're used. And in fact, if I take this hexadecimal, A691, like this, so that's my hex. Often in web lingo, you'll see all 3 of these bytes, all 3 of these 8-bit integers smushed together just like this. And in fact, if I go to a web browser and just do a search for this with a hash in front of it, it shows me this color swatch. This is how computers represent colors. And so the way this works is these first 2 hex digits, or hexets, I guess, they represent the red intensity, the blue intensity, or the green intensity and the blue intensity, respectively. And you can see them slightly differently, represented here in percentages and all sorts of ways that you can think about it. But that's the same color swatch as what Julia is representing for me here. Okay, so now we have an understanding of this. So now I can actually look at, my red of my image, right? My red image of, or like, so my image itself, when I look at it, Juno knows, hey, an array of RGB objects should be, we can display that smarter than displaying a whole bunch of numbers, right? But sometimes you want to look at the numbers themselves. And so if I wanted to look at, the red intensities of all the pixels of my image across everything, well, remember, if I tried to look at the red of my image, it's going to try to say, hey, it's going to try to look at the red of my entire array. But what do I want? What I want is the red of an individual pixel, the red of an individual RGB element. And remember, to do this pointwise, we use broadcasting. So I want to broadcast this across my image. And now suddenly I have a numeric array that doesn't display in my plots pane and instead displays down here. And it shows me my red intensities of my image. And I can do the same thing for RGB. So the green, I can do the same thing for the blue. And these kind of three panels get stacked together and displayed on our screen as you would hope as an image. Now, what's cool is we can use the images package to kind of put these things back together and make them images again. So remember, I have this red image that is a bunch of numeric types. The top right here is white, and white is represented by 100% intensity of all three images. The bottom left is muddier and darker. Those are lower intensity, and depending upon the colors, there'll be relative intensity differences. I can reinterpret this back as a grayscale image, for example, just by saying, hey, let's interpret all of these numbers as grayscale pixels. And there is the grayscale representation of the red channel, as you call it, of my image. Of course, I could do the same thing for my blue or my green here. Let's do grayscale of my green of my image. And that looks slightly different, right? And I can toggle back and forth. That's my red channel, my green channel, and you can see the relative intensities, right? Bill's face is a little redder than it is green because he's not sick. And so this green channel is darker in Bill's face than it is in the red channel. Conversely, the plant in the background here is green, and so there's not much red intensity, but there's much more green intensity. So this is brighter in the green channel. And this is how images work. They're just numbers at the back end. And I can actually put this thing back together. So let's create an RGB, RGB. So the red comes first, red of my image. And if I put zeros as the rest, then it'll display red, as you would kind of hope, right? Now I have a RGB image that only preserves the red channel. All the other channels are zeros or zero intensity. I can put my image back together. I can tear it apart, put it back together. So get my green of my image and my blue of my image, and I get my image back again. So here I've just torn apart my image into its three component parts, the kind of numeric arrays, and put them back together. Of course, then you can do fun things with this, right? Because these are just numbers, right? I can, for example, take the square root of all my red values. And that'll change the numeric values here, right? It kind of squashes them or does something funny with them. And if I do that in my image, well, it'll change what my image looks like, right? It'll suddenly give my image a red hue or like, subtly shift the color spaces. And this is how filters work, right? They're just doing numerics. It's kind of a cool thing. And Julia is such a great environment to play with this because it's so visual. And that's why I like this example, because it's a really visual way of looking at what's going on and playing with this. It's a lot of fun, right? So the title of this lecture is an image compression exercise, which is kind of a funny way of talking about images, but that's where we want to go with this, right? We want to use the numerics of our matrices, of our numeric matrices here, to do some sort of compression. So let's go back to my lecture notes here. This kind of talks about some of the things that I've done here. But now I want to talk a little bit about linear algebra. linear algebra is a core feature of Julia. It's a built-in, what's called a standard library. So it's a library that you don't necessarily need to have in your manifest in order to use. It's shipped with Julia. You don't need to download these packages. And you can use it just by saying, hey, let's use linear algebra. And that brings in all of the great goodies that the linear algebra package gives us. One of the big things about linear algebra in general, so for those of you who didn't do math undergrads or have the joy of taking a linear algebra course in recent history, my linear algebra is very rusty. It's been quite some time since I've taken linear algebra, but that's okay. The concepts here, you don't need to know the guts here, the theories behind this. The big thing to understand is that one of the games that you play in linear algebra is with matrices. And so say we have this red matrix, right? We have this red image, this red channel of my image. It's a 282 by 400 matrix with just a bunch of floating point numbers here. And those are just plain old numbers. One of the games that you can play with in linear algebra is what's called matrix decomposition. So it's taking a matrix, so let's call this red image our matrix A here, and it's taking this and what's called decomposing it into 3 component parts that when multiplied together will give you the same thing back again. So that's kind of a funny game, right? It's essentially saying, all right, well, let's take the number 24, and instead of writing it as 24, let's write it as 2 times 3 times 4, right? That's another way of writing the number 24. And we can write it as 2 times 3 times 4. And that's kind of the same game that we're playing here, only with whole matrices. And the trick here is that by cleverly designing the structure of these matrices, we can give meaning to them. And that's what the SVD does. So SVD is the name of a particular technique that does this kind of splitting of an array into 3 components that when multiplied back together, they give you the original thing. It stands for singular value decomposition. Again, you don't necessarily need to know the maths behind this. The key thing is that Julia provides it for you and that it takes one thing and splits it into 3 things that when multiplied together gives you the one thing back again. So let's see. Yeah, this is I messed up in creating this this notebook. I'm sorry about that. I'll have to write this by scratch. For some reason, this didn't load in properly when I converted this in preparation today, and my apologies. So I've said using linear algebra here, right? Linear algebra, that's what we need to do. And then we want the SVD. And you can actually ask for help here on the SVD. It gives you all the theory, all the things. It's a very long help function for a very short function name. But there's a way of doing this. And we want to do the SVD of our red channel of our image. So that spits out a lot of gibberish. The key thing here is that it gives me 3 parts, right? And I can do this with destructuring. So the way that you call these things is SVT like that. All right, and let's hide that. Okay, so using linear algebra. So these are the 2 lines of code that we need to do this. And this is how we split apart our image into 3 component parts, U, S, and VT. So now if I multiply these guys together in a particular way, I want to put S on the diagonal, and I want to do the transpose of VT, that should give me my array back. And what you can see is this approximately equal to the red of my image. It is. So awesome, we did it. We put it back together, we tore it apart, we put it back together, and we can in fact then go in here and see, so what does the gray of this reconstructed thing look like? Well, let me pull up my plots here. It looks just like what we had before. So this is how this works. There's a question, does Julia need to have the matrix in memory in order to do this? And yes, by default, the linear algebra operation does need to have this in memory. There are some distributed SVDs that can allow you to do it distributed. And that's in fact one of the main focuses of Professor Edelman's class is parallel techniques for linear algebra techniques like this. Another question about namespace collisions. So, we've loaded several packages, right? So this diagonal function and SVD come from linear algebra. Load came from images. What would happen if they both exported the same name? Well, the answer there is that Julia would warn you about that, and you'd have to explicitly say, hey, this shared name comes from a particular package. In general, most packages play quite nicely together. All right, so we've gone through this now, and we have our red channel split into 3 components, but this isn't doing compression, right? We've actually increased the size here. So let's just look in terms of the number of pixels. So we have a U element plus a length S element plus a length VT. So we have a total of 192 pixels in our decomposition, whereas if we just look at the length of our image itself, we're doing the opposite of compression here, right? We have almost twice as many elements as we did initially because we're splitting our single matrix into 3 parts. And we want to, and in doing that, we've extended the amount of information in each one. What makes this interesting and where this gets kind of cool is that there's structure in these 3 matrices that we've given back. So U, for example, is just it's a square matrix of 282 by 282 values. S is just the weights or the diagonals. And this is kind of like the relative importance of each component. VT then is 400 pixels long by 282 pixels. And the cool thing here is that this is essentially saying that this matrix is composed of a bunch of dot products that are weighted differentially. And so we can take the magic of matrix multiplication and matrix multiplication and do a small subset of this matrix. So we can take the first column or the first, let's say, I think it's this way, like to say the first 5 columns of our image, multiply it by the diagonal of the first 5 significant weights, or those weights that I had, multiply it by the first 5 columns of our other guy here and put that on the transpose. Let's see, oops, I want 1 through 5. So I did this wrong. I went to do a slice of the first 5 elements and I only did S of 5. And so I got a no method matching here. And again, this is what you'll often see. And it's telling me, hey, I tried to create a diagonal matrix with just a single value here. I want a matrix or a vector. So that gives me back my matrix. And if I interpret this as a grayscale image, oof, that's a very compressed Bill Kahan. But this is the core of an SVD. And in fact, if I play with this, so if I change this to just grab the first element here, oops, 1 through 1. This is kind of the most significant dot product in our image. And it's just taking that and spreading it across the entire image. Then the next one, and so on and so forth. This is how an SVD works. You kind of gain more interest. That's the second most important component, and so on and so forth, the third one. And as you add them back, you end up with effectively compression. So let's maybe do 50 components here. And there we have a nicer representation. Again, this is just the gray channel. We want to do this for all of our channels. So let's build a function that can do this for us. And I'm going to do this interactively here. I'm just going to, yeah, let's do it interactively. We do have this portion written out, but I think it's worth interactively writing this. So I want to create a function. Remember this from yesterday. This is going to be a bit of a recap from our discussion yesterday. What do I want it to do? So function compress image, and we take in an image. Let's call it just img there, and we want to return something, right? We want to end up with a value here. We'll return, I don't know, compressed image. So how do I get my compressed image, right? What do I do in order to do this? Well, I want to go through each channel of my image, and I want to compress it. I want to, do the SVD transform and then take a subset of these guys to give me a compressed version of this. So what do I do? Well, I want to reconstruct, I want to tear it apart and reconstruct it, right? For each channel. That's what I did here incrementally. I want to kind of take this and reproduce what I did in kind of a structured way that we can reuse. So what did I do first? Well, I did USVT, or kind of the common names that we use for that SVD of the red of our image, right? I tore apart the red channel of our image. And then I rebuilt it here by doing this. But I want to do a variable length compression. So maybe let's add a second parameter here, k, that'll keep the first k significant values, or singular vectors. So that gives me, a k-sized image. But this is, again, just for my red channel. Really what I want to do is I want to reconstruct this into an RGB of all of my channels, right? So I want to go through here and I want to reconstruct an RGB of this for my red, right? And then I want to do the same thing for my blue and the same thing for my red and for my green. Well, maybe I should create another function here that is, let's put it above it, kind of sequentially it comes first. Function compress channel. And that will give me so we can take in a channel of my image, so either red, green, or blue, and the K list of things here. And this is kind of a common sequence of events, right? We want to do something repeatedly. The moment you want to do something repeatedly, you want to put it in a function because that kind of bundles it up in a way that you can do this repeatedly. So how do we do this? Well, let's copy this out and put it in here. Now, instead of taking out my red of my image, this is just going to be the SVD of my channel. And instead of reconstructing it as a gray, let's just return this like that and return the compressed version here, the compressed representation of this guy here. So those are that option, or that way of doing it. So we're tearing it apart and immediately putting it back together. That's not terribly helpful, but you can imagine saving this as an in-between step, as a compressed version of itself. So what does this look like? Well, let's evaluate that, send that to our REPL, and then we can compress the channel of the red of our image like this, say for the first 10 images. That gives me back a matrix, right? And then I could put that into an RGB. So that means that I can use this down here, and I want to compress the channel of all of our three RGB values. So my red of my image with K components. I want to do the same thing with compress channel of my green comes next. My image for K components. And I want to do the same thing, compress channel for my blue of my image with K components. And that's all I return, right? I just put it together, take it apart, compress each channel. You can move this, shift that up, so that way it fits. There we go. So now I can define that. So now I can do an image compression and compress image of my image, say with 10 components each, right? And that will spit out a plot here. I can go back up to my plots pane. It's kind of blurry. I can do this, maybe with 20 components each. That's a little bit better. 30 components each, much better, and so on and so forth. Lots of fun to be had here playing with this. And the idea is, so the goal of this lecture is for you to gain familiarity with images. Images is a great package to kind of see how it leverages Julia's arrays in a different way than we've seen thus far, right? It uses a different element type that has pixels and colors, but those pixels are just numbers in the back end. And because they're just numbers, Julia can treat them like numbers, and you can do things like linear algebra on them. Which is a lot of fun. The other thing the other few key elements here that we're talking about is the definition of functions, right? So I just did 2 very short functions here, gave me a lot of capability. And this is kind of symptomatic of the way Julia code looks. Often in Julia, our functions are pretty short. Lean on lots of heavy duty computation and lean on broadcasting to do things to kind of distinguish between what's happening element wise versus vector wise and things like that. So remember, we're taking the red point wise of our image to give us the raw floating point values of the red intensities. And then we pass that entire array to our compressed channel function. And then that does the SVD, gives us this, and gets things going. So you can kind of get a sense of, so remember when I did that compression, when I saw the length of US and V as compared to the length of my image, we're not compressing it all by default. But when I do the kind of slicing of my U, S, and V here, that's when we actually get some compression going. And so if I look at, say for K, let's keep this like this. Oops, that's what I wanted to do. It's S of 1 through K and BT of colon 1 through K like this. So that is what we're doing. We've not defined K out here. Remember, it's only defined in our function. If we say, okay, let's look at how much we're compressing with 10 channels, we're effectively storing about 7,000 values out of our total length of our image, out of our total 112,000 values. So we're looking at 6% of our image size. And that looks pretty crummy, right? Compress image with 10 values. That one looks pretty crummy. So that's what 6% of our image representation looks like. The goal here isn't to teach you how to do image compression. In fact, this isn't how you would want to do image compression at all. You would want to use a specialized image technique. The goal here is to kind of show you how the generic programming of Julia allows you to use some cool things and mix and match between ecosystems. So from linear algebra to images, the same kinds of techniques are true everywhere. You can kind of mix and match techniques, play with things. And it's kind of because we try to limit the number of idiosyncratic representations. Images just uses bog standard arrays, the built-in arrays, as what a picture means and what it's doing. And so that is, yeah, I think that gets us in good shape now. We are towards the end of our hour here. Hopefully this was helpful, right? The goal here of this exercise is to be kind of a synthesis of a lot of the techniques we've talked about yesterday and today. And that puts us in good shape for the rest of the day today. So we're halfway through our course now today. The remainder, we'll talk about plotting. And then the rest of the course, we will kind of take I'll happily talk to you all about individual things. The rest of the notebooks can be a little bit shorter. I do want to talk to you about types. So we've really not talked about types or multiple dispatch. Those are some key features of Julia that I'll want to talk to you about yet. But the rest we can kind of take it as it comes. There's a request already for HTTP endpoints and kind of setting up APIs. We can talk about how that looks. And yeah, I think that's a good summary. I'll go back to my my code here. I can actually copy and paste these two functions in the chat, so you don't need to type them out yourself if you don't want to. But I encourage you to play with this, kind of see how this works. Yeah, we'll do multiple dispatch. We'll talk about that. That's a huge, huge part of what makes Julia Julia. Any other questions about images or where we're going? And I guess during this break, if there are other topics that you want to see covered in the last 2 hours, please throw them in there. I may not have time to get to them all. There's a lot of depth, of course, as you can see, and so we can do this. Nice. Okay, PyCall, we have a notebook ready for that. Lithograph.jl. I'm not familiar with that package.
I keep spelling it wrong. I meant light graph.
Oh, light graphs. Yes. Okay. I've not done too much with light graphs, but we can take a look at that too. I don't have a tutorial set up for that off the top of my head, but we can take a look and see what that does. Okay, with that, let's take our 10-minute break, and I'll see you all back here at 6 past the top of the hour. All right. Welcome back, everyone. Excuse me. There was a request to show my REPL around where we were compressing things. So yeah, I was playing with, setting these things up, and then you can compress your image, pass in the image. I don't know what you're after, Vish, there, but hopefully that's helpful. You can give me a little bit more. Okay, good. All right, so the next thing that I want to just quickly go over is plotting. I'm not going to go too in depth here because there's a lot of things that I want to talk about. And we've already talked about some of this, right? We've already added the plots to our package environment when we were talking about packages. And we can just go in here, execute. Oops, I just executed the entire file. That's not what I wanted to do. This is one of my gripes with VS Code is it's very easy to execute the entire file. What I did there to stop this, and this doesn't always work, but it's a decent thing to know about, is Control-C when your focus is in the REPL here. If you click on the REPL and then hit Control-C, it should stop your execution. It looks like it didn't quite work this time because it's still going. Yeah, there it goes. Okay. All right. So yeah, that's one of my gripes with VS Code. It's very easy to accidentally hit Shift return instead of Control return or Control enter, which was what I wanted to do. So I just wanted to say using plots. And we'll just quick look at a very simple little plot here that allows us to play with things. We're going to use a very small data set. Plots, of course, can support very large data sets. We're just going to use two 6-element arrays here, an array of global temperatures, an array of pirates. These are at random time points between 1860 and the year 2000, how many pirates there were and what the temperature was in Celsius. Plots supports multiple backends. We can talk a little bit more about that towards the end of this section. I'm not going to talk too much about it now. GR is the default backend. You don't need to know what that stands for. It's just kind of the drawing library that does the actual drawing of the image. The key thing, though, is the plot command. And plot will take in your number of pirates and your global temperatures, and you'll set it up as with your current label, or you can say there's a bunch of keyword arguments here. So again, we're using positional arguments and then keyword arguments. And the positional arguments, like I talked about yesterday, that's kind of like the data, right? And then the keyword arguments describe extra bells and whistles that we can do with things. And so this is the key functionality is just the plot function, which will do a line plot of all of these things. Shucks, by executing the entire thing, I did actually end up changing my backend. So I want to hit this GR to plot it. And again, I'll pull up my plots window. One of the helpful things you can do with your plots window is grab it if it's not already. You can grab it and stick it to a pane on its own. And so I want to put my plots pane in a separate plot here. And let me clear a bunch of my things from the images session. I'll just hit the delete trash can a bunch of times. And let's plot this again. Okay. So here we go. So here's my plot. It looks a little bit better if I'm zoomed out a little bit, but then you can't see this, but you can kind of get the idea here. It's set up here and it's kind of scaled so that way with a normal size window, it looks right? Like when I'm not super zoomed in for you all to see my screen, this looks correct. So you can see it plotted the number of pirates and the temperature here on the x-axis, and it just did kind of like a scatter plot connecting them with lines. Yeah, we'll record. We're recording this, so for those of you who need to drop in and out, you can come back and look at these things. Sorry to miss you, but hope you can stick with us or come back. So yeah, apparently we have some sort of an agenda here that we're trying to sell, correlating number of pirates and the global temperature. To do this really well, let's add a few more things to it. So we can change my plot with the scatter function that updates it to include points. So executing this line of code here will add a bunch of dots along with my line so that, you know, and we're labeling them so you have multiple series. And this is how you can add multiple series to a plot. It's somewhat interesting here that we're using a bang function, right? And what would happen if we were to run this line of code without the bang? Like, why are we shouting at Julia again here? What happens if I were to just change this and run this without the bang? Well, oh, weird. Oh, it's because I have a P there. If I run it without the bang, I just replace my plot totally, right? I've created a new plot with the number of pirates and the global temperatures. And then I can go back and do the line plot. You know, by default, the plot function does lines, the scatter function does dots, but they're replacing each other here, right? And if I change the scatter to a bang, instead of that, and go back to my plot and do scatter bang, well, then it's now updating my plot object. And this becomes more clear if you use what was written here initially, which was that P, this plot object. You kind of are updating this plot object, and that's an optional argument. By default, it'll just reference the global plot object, the most recently plotted thing. And so it's kind of a nice way, but you can also be explicit about what you're plotting here like this. So that allows you to do these things. You can get this up and running pretty quickly and easily. And you can always just show this plot again by hitting P, right? And it'll, when you execute P at the REPL, just like images work, right? P here is, you know, you can ask what is the type of it. It is a plot object, and it knows that when it's displaying in VS Code, not to display gibberish, not to display anything at all in text, because it's a plot that we want to see. And so it knows to communicate to VS Code to put it in a plot pane like this. We want to, you know, add some legends and things like that. And again, we're mutating or updating our global plot object. So we use xlabel bang to say, hey, let's add an X label. Let's add a Y label. Let's add a title. And each time I do that, I'm, you know, returning a new plot object each time, and each time it's displaying it here in my plots pane, and I can go back and forward and kind of go back in history, go forward in history, and watch my graph evolve, which is kind of a nice feature of VS Code, is that it holds on to that history of all of my plots, and it does so without, you know, taking up too much space. Each plot here is just like 100K or so, probably. It's very limited overhead for some nice functionality. But like I was talking about, we want to sell an agenda here. It's kind of looking like our number of pirates is decreasing, as is our global temperature. Let's flip an axis. So there's just kind of a simple command where you can flip the axis. Now you can kind of drive a point home that global warming is caused by pirates decreasing. We need to bring back the pirates. So this is a very, very simple and minor toy example, but the point here is to just give you these things. The question, a good question, is how do we know that we're updating this P plot? And it's because actually, if we look at xlabel here, just as an example, let's see. So the documentation is somewhat anemic here. It doesn't say what methods there are. I can ask Julia what methods are there, and we'll see how this works, right? So the first method here is where we label with a string, right? We pass in a string and potentially some keyword arguments. The second method here takes in a plot as its first argument and then a string. And so what's happening is when we X label, so let's go back up here so I can change, actually let's do Y label. global temperature. Let's add in a degrees. Let's see, degree C there. Let's see, yeah, it does support Unicode. Nice. So I just added, changed this, updated it. I can explicitly say, mutate the P graph, that P object that we created. If I don't do that, it automatically does this by looking for the global plot object. They're the most recently plotted thing. And it's kind of fun to see this, right? We can actually ask Julia to edit it and open this in my editor. Oh, I have my editor set up as something different right now. Let's see, can you open up? Maybe. Why aren't you going? Where'd you go? Oh, I lost my screen. There we go. There we go. So I edited it, and if you just do the Y label and you don't pass in a plot, then it automatically fills it in. That's all that's happening there. Yeah, it's not as clear as I'd hoped, but it's just working with the global. If you want to save this plot, it's as simple as save fig, and you can pass in the plot object, and it'll automatically figure out what kind of figure you want to save based on the file name that you pass it. So I could say my agenda.png, and that will create a file here that is a ping, an image with a ping extension, and it's saved there. I could, of course, open that thing up. I could load it even with the images package, right? And then it would load as an image. I can also save it, I think here, let me just see here. It can be sometimes nice to save it as an SVG instead, and that's also supported. So now I have both ping format and SVG format, and it just kind of automatically figures that out based on the file type that I pass in. And so if I go to my file here, my agenda.svg is the SVG version. The ping will, of course, show up here as well. And you can save these in all sorts of different ways. There's a lot of depth to plotting, as you might expect. And to get more information on that, we can go to the plots.jl package, and the documentation here is pretty awesome. There's a lot of examples. There's a lot of things that you can go in. There's a nice tutorial about, shows the simple plots, but then also gets to more complicated things, subplots, bar plots, scatter plots, all the things that you would want, histograms, fun things, partial histograms, heat maps, violin plots, lots and lots and lots of depth here. I could spend an entire course talking about this, but I just want to be able to point you to this and look at this. Another question privately in private chat was about three-dimensional plots or contours. Those are also here. Let's see, there's a surface command that's, let's see, where is this? I guess some of these are kind of dependent upon what backend you're using. And I'll talk about that a little bit more in just a second. But there's, pie charts, polar charts, all these things. There's also some really cool support for animation. So you can create GIFs and lots of fun things there. It's as simple as a for loop. So here you can look here. This should look fairly straightforward, right? There's one special thing here that we've not talked about yet that's just kind of setting up the layout of my plot. But you can see how we set up the plots. We do line plot, a scatter plot, and then we loop over a range and we plot these guys and just set up a frame of an animation. And plots will automatically bundle this together, create a GIF for us that you can do fun, nice things with. Let's see, and then surface and 3Ds are also down here too, I believe. Oh, do we not have an example of that? Maybe we don't. Yeah, it's there. It's just there's not an example. These plots are all automatically generated, but that does work, and it is, you can do 3D plots as well. All right, I think that's about what I want to talk about there. Any questions about plots or anything in particular that y'all would want to see? Oh, there's one last thing I want to talk about. You can put your questions in the chat if you have any. And that's the ability of switching backends. And so there's a package that you can add here called Unicode plots. We haven't used this yet, but it's a very, very small package, so it's not hard to add. You can, let's make this a little bit bigger again. Oops, too big. And I can collapse my plots pane. Okay, so you can add Unicode plots. I've already run this, so it's already there. Use the Unicode plots function to kind of switch what plot means. Essentially, this is reaching into the plots library and saying, hey, instead of drawing an image, I want you to do something different. And in this case, we will draw things directly in the REPL using ASCII, which is pretty cool, right? It's just setting up our plot and drawing our lines exactly the way that you would in an image. This is really, really nice for quick and interactive debugging, right? You have very, very quick and easy debugging capabilities here. And if you're not in an environment like VS Code, or if you're working over SSH to a remote computer, it's really nice to be able to look at your data really quickly and kind of summarize it really nicely, just directly in the terminal. So you can do all the same things that we did before. And the cool thing is that the API is exactly the same, right? This looks exactly the same as what we did before. We can add points to it. We can add an X label, add a Y label. We can add a title. And now you can see here, this is our graph, and it's nice and bold with some blue points in there and the green line. I guess the blue and green, it's kind of hard to see. That guy's blue, that guy's blue, and so on and so forth. But it's using Braille dots to set this all up and giving me my graph nice and easily in the terminal. I like this especially for bar graphs. Like if I do a bar of a random sequence of numbers, or I guess a histogram is the one I want. It will, display these things nicely, kind of draw them nicely. I guess it's if I use Unicode plots histogram directly, it ends up looking significantly different and will bin them nicely for me. So there's lots of different ways of doing this. I love these kinds of things for interactive graphing and bar graphs. It shows me my frequencies, everything that I'm doing here. So that's Unicode plots. Just another plotting package that plugs into the plots API. So you can use the same API, you can use its own package names. And here I'm using the explicit referencing. So I didn't say I'm using Unicode plots here, it's imported instead. And so that's how both plots exports the same name, right? We had this question about what happens with different names. So plots will do this in a different way. It's kind of more general, right? This is the histogram of my data this way. And it plots it kind of looking like an image drawn with plots. But if I ask Unicode plots to do it directly, it will do it in kind of a more Unicode friendly way. And so both of these packages export the histogram function. If I were to say, hey, let's using Unicode plots, it'll actually give me warnings about the things that conflict. And then if I were to try to run these things without qualification, oh, interesting. I guess it doesn't. in some cases, it'll throw an error if it's ambiguous about what's going to get called and how that works. I think it depends a little bit on the state of my session as to whether that error pops up or not. In this case, I think it's because I've already called histogram that Julia is saying, oh, you've already called it. This is what it means. It's not ambiguous. Had I stopped and started again and hadn't called it yet, then it's suddenly ambiguous whether I want to mean the plots version or the Unicode plots version, and that's where it'll throw an error for me. So that's that. I think at least for a while, so we have my, let's see, let's do this, oops. This plot here. XFlip for a long time wasn't implemented in Unicode plots. Yeah, I guess it's still not implemented there yet. So some things you'll see like that, like we can't get our final image exactly the way we had it before because Unicode plots doesn't support flipping the axis, at least not yet. Hopefully someday it will, but that's one slight caveat to be aware of. Any questions here? There's some exercises here. They're pretty simple and straightforward. You can play with them if you want, but I think let's move on. Okay, so Notebook 9 is just a little bit of a horse race, talking a little bit about the performance model of Julia. It's a fun one to walk through. It talks a little bit about floating point addition, summing numbers, and doing it the fastest way possible. I think I'm going to skip that one. You can always go back to it and run over it. It's a pretty self-sufficient notebook, and it's one we've used for a long time. So I'm going to skip this one because there's a lot more to talk about, and I think let's dive into multiple dispatch. So this will get us to a point where we can really start talking about all the capabilities of Julia. And I think this will be much more beneficial to you all than trying to sell you on Julia's performance, which I don't think you all need sold on. So let's do this. So I opened up Notebook 10. That will set this up. I'm going to close my plots pane because I'm not going to use plots for anymore. If I were to plot anything again, it would pop up for me again, but we don't need it at the moment. So let's talk a little bit about multiple dispatch. And multiple dispatch is at the heart of what makes Julia Julia. It's a very key feature and a great thing to gain an understanding on. So thus far, we've defined some functions. For example, we've defined this function, right? We've defined a function that will square its input. And you can square the number 10, right? And we talked about how this can do duck typing. You can square a string because multiplication is defined on strings and strings know how to do that. You can square a matrix, right? Because matrix multiplication is defined. You can't particularly square a vector because that's not a defined operation. And so that's kind of how this works. And you'll note that if I square this, I end up with a no method matching function where we got inside the square function, right? Julia happily walked inside the square function and then tried to do the argument raised to the second power, exponentiating it. And at that point, Julia threw an error and said, hey, I don't know how to exponentiate this. And we talked a little bit about these no method matching errors and how they're common and something you'll see and a good thing to learn how to understand and read. But what's happening here is actually, multiple dispatch in action. And it's because of this capability of specifying our input types that you could explicitly say, hey, I only want this method to apply to a certain set of function or a certain set of objects. So let's take a step back and define a function f that only works, that takes 2 arguments, right? And so we've seen the ability of writing a comma b equals something like this, right? We've done that and written it. Here we're adding a new syntax, a new notation where we're using double colon integer like this, double colon integer. And what that double colon means is it's kind of saying f where a is the argument name and its type has to be of type integer. B is an argument b name and its type has to be of type integer. And then we can say, hey, a and b are both integers. So we can define this and we get a and b both integers. We have this set up and now we can call f, right? And just like before, through f of 3 and 4 returns the string that just says, hey, both my arguments are integers. If I try to do something like 3 and 4.5, that's going to give me a method error, right? Julia tried to find a method that it could use to call this function, but it says, hey, I don't know how to get an input of an integer and a 64-bit floating point number. The closest candidate would be if that floating point number was an integer instead. And it nicely highlights that for me. You can see here, these things are highlighted, and you can actually even see that this f here was defined at my REPL in the 199th thing that I've entered in my session so far. It knows about that. And so you can go in here, or if I used 2 floating point numbers, it says, hey, neither of these guys were applicable. And it gave up, and threw up its hands. It didn't even try giving me a closest candidate because none of them were partial matches. But you can see here, it's saying no method matching where we have a float 64 and a float 64. Well, we can define that method, right? We can explicitly say, tell Julia what to do if A and B are both float 64s. And if they're both float 64s, then we know what to do, right? We can do f of, we can call that function, and now that function is defined. So whereas before this gave me a no method matching error, all we needed to do was incrementally define that function, and now suddenly that's no longer an error and it works for us. So this is kind of the heart of multiple dispatch. We can actually look at F and see what methods are available. And you can see that we have 2 different definitions of how to do this F operation, whatever this F operation is doing. We declared this, and we didn't overwrite the integer method when we declared the floating point method. It kind of layers on top. It adds an extra method to the function called foo, and that's the language we use. And so when I look at f here, it prints out and says f is a generic function with 2 methods. So there's 2 different implementations depending upon the types of arguments that we pass in, and it'll use whichever one is applicable. Of course, if I tried to call f with 2 strings, f of hello and world, that's going to give me, again, a method error with, says, hey, I don't know what to do when I get 2 strings. And again, you could define that and keep moving. So, we've seen methods of F. This kind of structure underpins all that's happening in Julia. And so just kind of as an aside, this is built into Julia, and pretty much every single Julia function has multiple methods on it, has multiple declarations. So how many methods do you think there are for addition? Just take a second and think about this. So how many different ways can you add things together? You have numbers, maybe integers, matrices. I don't know, how many ways are there? And the answer is there's a lot of ways to do this. Right now in my current session, I have 264 methods. Depending upon what packages you've loaded, You might have slightly more, slightly less. If you've been playing around with me and done things in a slightly different order, you might actually see a different answer here because it depends upon what packages are loaded, and each package kind of defines its set of operations. And so if you kind of scroll through here, you can see, oh, you know what? You remember we were working with colors, and there's a way of adding. Here's a method that looks somewhat familiar. You can add together RGB objects. And in fact, it's defined in a slightly more abstract way. So there's a understanding of an abstract RGB that encompasses some more behaviors, but there's a way of adding colors. And our images package, through one of its dependencies, has taught Julia how to add colors together. And so now that is supported on the plus function in my current session. It's kind of cool, right? You can keep scrolling up here and see all the different things here. Let's try to find another one that's somewhat readable. There's a lot of things here. Here we go. So a bunch of numeric ways of adding things. So adding a real number and a complex number and a real number, integers together, integers with rationals, all sorts of combinations here. And this is, the heart of multiple dispatch. There's tons of these things and lots of ways of asking about it. The kind of, this complexity here can be a little daunting. There are some tools that makes it a little bit easier. So there's a macro, and we've not talked too much about macros yet. But macros start with this ampersand sign, and they're just kind of like a special keyword to the language. And you can ask, what method gets called when I add two integers together? And here you can see that there's this fancy method. We'll talk about how to define a method like this in just a second. But there's some fancy methods. Or what happens if I add an integer with a floating point number? And it turns out there's a generic way of adding two numbers together. And where it's defined is actually kind of, it gives you a hint as to what's going to happen, right? It's defined in a file called promotion. So maybe there'll be some promotion that's going to happen within that function as it goes about figuring out how to add them together. So how does the system all work? How does it all layer together? Well, let's keep making this f function. So remember, we have our methods of f. We just have two methods on it right now. Let's make it a little bit more complicated so that way we can play with this a little bit more. So let's add a method without any types on it. And when you don't have types on a thing, then it's the same as saying that this is an any and this is an any. So any, remember, we use this for our arrays. It's a union of all types. It can be any type at all. And so the shorthand without having a type annotation is exactly the same as saying, hey, any type can be applied to this. So you can pass that to our REPL. We can define a few more. So if they're both numbers, this one's a little bit more interesting, right? So A is a number and B is anything. So we can say something about A as being a number. If B is a number and A is anything, we can say something about B. And then we had this integer method that we had already defined. So now we can look at our methods of f. We've added a bunch now, right? Still not the 200 some that plus had, but there's some more complexity here. You know what to do when they're floating point numbers. And we can play with this a little bit, right? If you have a floating point number and an integer, which method is going to get called here? Well, you can kind of work your way down this table and see what's going to be applicable or what's going to match this, right? So could this call match this first one? Well, no, because the second number here isn't a floating point number, right? This is an integer and this is a floating point number, so that doesn't work. The second method, well, no, this is a floating point number, but this is an integer, so that doesn't work. Aha! But they are both numbers. And we've not talked too much about the type hierarchy here, but this is kind of leaning on a type hierarchy where there are abstract types and super types and such. We don't need to dive too deep into that, but the general concept is that we have these abstract classes. And as you'd expect, a floating point number and an integer are both subtypes or are generalizations of a number. So it should call this third method where they're both numbers. And if you execute this, sure enough, it'll tell you A and B are both numbers. If you do an integer and a string, well, the first argument would match here, but not the second argument. The first argument would match here, but not the second argument. And you go on, and aha, the fourth argument would probably get called, right? And you can do that here and see, yep, A is a number. So that's this method. And the cool thing about these method tables here is that they're actually sorted in specificity. And so you always call the most specific option that could be available to you, right? This call here with an integer and a string, they're also both anything, right? And so theoretically, this method could also apply, but we've added in a more specific method, right? The fact that A is a number is more specific than A could be anything at all. And so Julia thinks that it reasons that it's probably more applicable to call this more specific option. And so you can reason about these method tables by working your way down them. They're sorted order, and you'll call the first thing that appears here. And that's kind of a handy little trick of reasoning about what happens. I could, again, also just ask, which method gets called? And sure enough, it's the number and nothing there. And so that's how that goes. There's a few more examples here, right? If they're both integers, it calls the integer method. If you have a string and an array, well, we haven't defined anything for strings or arrays at all, right? There's nothing specific about strings or arrays that we've taught Julia. And so we just hit this fallback method that can accept any type. And so you get the fallback behavior. That's often the verbiage that we use here. The most general function is kind of considered to be the fallback because it's the last thing in the method table. It's what you'll always hit. And so it's the fallback behavior, the generic behavior that you end up using there. There's a few interesting cases then that happen and fall out of this. So if I create another function named g and just define two methods on it, right? So now I have a g, which is a generic function that just has two methods. The first method is specific to an integer. The second argument is a number. So when A is an int and B is a number, we print out the number 1. When A is a number, but B is an int, we print out the number 2. So you can test this out, right? You can ask what the methods are here. Methods of G, prints them out nicely. They're, again, in order there. So what happens if I do an integer and a floating point number, right? So an int and a number here, we get the first method that we defined, right? This method that gives me the number 1. That makes sense. If I do the converse here and just print out 1.5 comma 2, that gives me the second method, right? So 1.5 is a number, it's not an int. 2 is an int, and so we get this method. Now, what's going to happen if I were to call g of 2 comma 3 here? Both of these are integers, right? They're also both numbers. And so which of these two methods should be more specific? Well, A is an int and B is a number. B is an int and A is a number. And these two things are kind of mutually equivalent, right? Why should this one get sorted before this one? You might think that it would just return the first one. Remember what I told you, that they're in sorted order. You just work your way down the method table. And so you might think that you're just going to get this first method here that would print out 1. But what actually happens when you call this? You end up with an error. And this is interesting, right? It prints out a method error, and this is a different sort of method error than we've seen before. It says, hey, when we pass in 2 ints here, we're in an ambiguous situation. These two methods are of the same specificity, you could say. They're equally specific. There's no really good reason why this one should get sorted before this one, or vice versa. Julia helpfully prints out what the two candidates are here, right? It says, well, it could have been this one or it could have been this one. And even more helpfully, it says what the fix would be here. And the fix is simply to define what happens if they're both int64s. It happens to be that that's the intersection of these two argument signatures. And that is a really nice little feature here. And so we can define this, right? We can say, we can just copy this error message. This is actually pure like fine Julia code as it's written in the error message. And we can say, hey, if they're both integers, we'll use 3. Now, a little kind of fun trick here is that I didn't actually name my arguments, right? What I've done before is I said argument 1 was named A, argument 2 is named B. Here I didn't name them. I just said what types they were, and that's fine if I don't need to refer to what the arguments are. And sometimes that's useful in dispatch or in choosing which method you end up calling. So now if I call that G, 2, 3, I get that third method that I just defined. I no longer have an ambiguous situation because in my methods table, this one is more specific than this ambiguous pair. And that's the language we talk about this here, is that this pair of methods are ambiguous with each other. Julia tracks that. And it's an error if you run into that case. In general, you don't see this too often, and it's not too big of a deal. If you do, it's pretty easy to see, oh yes, I just need to teach Julia what happens in this certain case. So then let's see. So that is ambiguities. There's one last kind of cool thing here that is fancy syntax. So if we go back to our F method, remember we have these 6 methods that we defined on F here. You can introduce what's called a type variable, or I like to call it a wildcard, that matches both arguments simultaneously. And so this is a little bit of a fancy syntax. And what we're saying here is we're going to define a function where A is of type T and B is of type T. And we're just using T as kind of a placeholder wildcard and saying, hey, it's going to be in cases where T matches a number. And then we'll print out that A and B are both of type T. And here we're interpolating T into our string. And so we can define this, right? And we can ask for methods of F. Now we've defined a 7th method, and it just inserts itself here, and it knows what to do if they're both of type number. So if for example, I say F of 1.5 and 2.5, or 1.5, 2.5, like this, it knows that they're both float 64s, and it hits this method. And it's more specific than if they're 2 different numbers, right? If I had 2 different numbers, then I end up, with this thing, and it wasn't able to match a concrete type in this kind of wildcard matching paradigm. So I can do it with float 64s. I could do it with, say, we talked about rational numbers, 1/2, 2/3. They're both rationals. We could do the same with, say, complex numbers, 3 + 4 imaginary, right? They're both complexes. This is kind of a cool way of defining a whole suite of behaviors. It's kind of like a template, right? Where you're defining what to do for a given type, and you can have access to that type in your argument body. You know what that type is, and that's how that works. You can play around with this and do lots of fun things here. I think that's all I'm going to say on that. There's some more depth here in how you can do this, but that's the basics, and this is the basic syntax, right? It's this where clause that introduces the wildcard. The one thing to note here is that there's nothing special about the name T. T is just a very, very common stand-in for a type. It's kind of like how we often use the capital letter A for a matrix, or the lowercase letter I for an a thing that you're iterating over in a for loop. It's one of those idioms. This could just as easily have been, a wild card type like this, and then I'd have to change both T's here to be wildcard type. That's the same thing, just a whole lot more verbose. The other fancy syntax that we're adding here is this kind of funny face. And if you want to ask Julia what it is, well, you can just hover over it. And VS Code will tell you it's help, right? This is the same as asking for help in the REPL, but it's kind of a nice and easy way of seeing it. And it tells you, well, it takes 2 types. And again, remember that capital T is kind of a shorthand for type. And so if you see that in Julia, it often represents a type, T1, T2, and it just asks if, we have a subtype relationship. So if, there's a subtype of number. So a good question from Vish is, so these are all dispatch on types. Can I dispatch on value? And the answer there is no. The Julia type system is entirely geared around types, and dispatch is entirely geared around types. So if you want to dispatch on value, you do that just with an if statement inside your function, right? So if you wanted to add f function, a method on f, something like this. Let's say a is what haven't we used yet? Let's do string. B is a string, and you want to dispatch on the values here. You just say, hey, if a is equal to hello, then do something. Oops, I need double equals here. Then you can do something here. Else if a is equal to some other string, right? You can keep doing this on and on and on. Oops, else if statements are combined like that. That's how you can go about. And values are checked at runtime. It's part of the runtime behavior of Julia, whereas types are part of the compile time behavior, and that's the strength. You can do some fancy things, like you can put a value into a type. And we've already seen this, actually. It's kind of sounds a little bit crazy, but remember what the type of a matrix is, right? Or a type of a vector. It's an array with a parameter, and the parameter's value is of type as an integer here of 1. And so I can actually add a method to f here that specifically deals with vectors, or specifically deals with one-dimensional arrays. And I can say, hey, let's add a method on f that specifically works with an array of int 64, and that is one-dimensional. And here I'm actually doing kind of like a value-based matching, right? It's going to match exactly that type. And I can say got a vector of integers, right? And so if I call f of 1, 2, 3 like this, that'll match. And it says, hey, I got a vector of integers. And that works and works just fine. If, however, it's a matrix, remember that the type of this is going to be different, right? And so if I pass in a matrix, it's going to say, hey, I don't know what to do when I pass in a 2 here, if there's 2 dimensions. You could have meant something with 1 dimension, though. Maybe that's what you're after. And that's how that goes. So just to wrap up this one little discussion about values in the type domain, you can actually create your own types that are parametric and have values, and you can kind of exploit this behavior in a nifty way. And we have a built-in type in Julia that does this, and it's called the val type. And it'll just take a value and put it as a type parameter. And so in this way, you can actually do kind of sort of dispatch on values. It's a little bit of a workaround that does what you're after, but often it ends up adding overhead instead of removing it. And so that's why I don't point folks to this very frequently. You can ask for help on val, and it tells you a little bit about how to define functions that dispatch on them, and a little bit about what's going on, but it's kind of a way of hoisting information to compile time. So a really good question about this, what's defined in the notebook here. There's this another method or we define a second function here, FF, and just kind of as a placeholder, just kind of play around with this. And here it's saying A is a number and B is a number, but FF of 1 and 1.0, that doesn't work, right? It says, hey, there's no method matching this. And the answer is that this wildcard matching functionality only applies to concrete or the kind of like the most specific data types. And so number is abstract. It's kind of an abstract representation of lots of different things. And it won't match, it's not the same, for example, as saying A is a number and B is a number. And if you can define that if you want to, but we found it much easier to define this to mean that it's got to match an exact representation. So that being, a set bit integer width, or a set floating point width or things like that. So similarly, right, you can do FF of 1.0 and 2.0. Those are two floating point numbers, right? Or 1.5, 2.5. Those are both floating point numbers. I can do the same thing with float 64s. Remember, you do that fancy scientific notation with an F to write float 32s in Julia. I can do that. But if one is a float 32 and one is a float 64, these two things are of different concrete types. They're different, leaf types or the kind of the type hierarchy. And so that's not going to match this wildcard. This wildcard, even though these are both floating point numbers even, they're not going to match that wildcard. You can ask a little bit about this type hierarchy so we can dig in just a little bit more. And we can ask for, what's the super type of a float 64? That's an abstract float. What's the super type of that answer? So by default at the REPL, this fancy ANS name gets assigned to whatever the last answer was. So you can easily walk up a type hierarchy this way. And you can see that a float 32 is an abstract float, is a real, is a number, and it's that anything. And any super type of anything is always anything. And so that's how that works. So yeah, you can actually have multiple wildcards here, and you can do all sorts of fun things with it. So let's do that here. So we can add another wildcard here. Let's make this a little bit more complicated. So let's do C and D. Let's add, say this is, S is kind of a common name for whatever type comes after type T. So where T is a number and S is a subtype of, let's just say it's a subtype of anything. So S can be anything here. C and D are S. There we go. So now I've defined a 4-argument function, right? And 1, 2, 3, 4. The first two have to both be the same kind of number. The second two can be the same kind of anything. So to call this guy appropriately, so 1, 2, those are both numbers that are both integers. 3 and 4 can be anything. So let's say S1 and S2 for 2 strings, right? Like that. And you can see here, pardon my misspellings, but you can see that we have A and B are both integers. C and D also simultaneously matched separately and independently of the T wildcard. And these things can nest. You can do all sorts of fancy things here. So yes, there's lots of things here. And you can even, one of the most common places to do this is with arrays. And so one of the important things with Julia's type system, and this is something that catches folks out in many cases. So if you look at, so remember we have our vector. Let's create a vector here that's just 1, 2, 3, 4 like this, right? So we have an array of integers that's one-dimensional. You can ask, so what is the super type of this guy? And this is the whole thing is a type. We can do the same kind of thing. Super type of this array is a fancier kind of array, right? And we can do the same kind of walking up the type hierarchy of our arrays it's an abstract array, and it's an any. And so you can see that this integer and the number 1 have kind of followed it along. It's an abstract representation, but then it gets lost when it becomes of type any. And so that's a little interesting there. If I wanted to define a function, so let's see what I have. So methods of f, I defined, remember I went in here and defined a function on f, or a method on f that works for vectors of integers, right? If I want to call that, I can call f on my vector, and that works just fine. I got a vector of integers. That's what I want. But what if I did this with a vector of float 64s, right? 1.5, 2.5, and so on and so forth, right? Now it's a vector, it's an array of float 64s. So that doesn't match this type. And it's kind of like not matching with a matrix. Same idea. Now we're not matching the element type. And I defined my method f very, very tightly, right? I defined it as only taking an integer and nothing else. So how would I fix that? Well, I could try fixing it by adding another method to f here, f where a is an array. And maybe let's just try changing this to anything. Got a vector of anything. Seems like that might work, right? So let's define that, and let's try calling this again. That still didn't work. So why not? Well, it's matching this float 64 exactly against the any here. And this is a little bit of a tricky part about Julia, in that the type parameters are kind of unlike the types themselves, and they need to match exactly. And so I can do this. There is an object that I can pass to this that would give me a vector of anything. And that object is a vector of anything. So if I have an array that happens to contain a string with my name in it, a complex number, a bunch of different things, these things can't promote together. And so Julia will actually create an array of anything. And this is kind of like that Pythonic list that can contain anything. I can add anything to this. Remember that from last time. So if I call f on this array here, now I actually matched that method. This is exactly what that was. This is exactly that method. Okay. So how would I match a vector of anything that actually might contain, like say this 1.5, 2.5, and the answer there is with a wildcard. So let's define yet another method on f, and let's add a wildcard here, t, and where t is a subtype of any. And now we can pass that in there like that, and now this will work as I expected. It's a vector not really of anything, it's a vector specifically of float 64s, right? And this vector can only hold float 64s. It has a specialized representation for float 64s. That's why this is important in Julia to have this. And this is another case where you'd use this wildcard matching sort of thing here. So this is a little bit in the weeds, but it's something that folks run into very, very frequently, and they'll see this commonly, is that they want to accept an array of any type or a vector of any type, and so they try to define this function for us and run into trouble there. Let's see. Oh, we're at the top of our hour again. I'm almost done with this section, and then the last hour we can talk about advanced topics and do a bunch of fun things. One last thing that I wanted to show here, and one last snag that happens with this f function, is remember we have these specialized range objects that kind of sort of work like vectors, right? I can do fun things like square each element. Remember that, the dot exponentiation to square each element, and it behaves like an array of the numbers 1 through 4, right? 1, 2, 3, 4. I can index with it. I can do all sorts of fun things with these things. But the one thing I can't do with it, at least not right now, is call f on it. Because I've defined f to only work for arrays. And remember, I asked for, when I looked at the super type of an array and the super type of its ancestors and things like that, there's a whole abstract array hierarchy, this kind of understanding of, hey, it doesn't really matter what the exact implementation of my array is. I have a lot of array-like objects, and these array-like objects are really powerful and a key part of Julia. And so, for example, this unit range, it only holds 2 values. It only knows about its start and its stop, and it kind of on the fly creates all of the things in between as it needs to. So you can index into this thing as you would want to. You can ask for its length. You can ask for its size. You can do all the things you would want with a range. You can, multiply it by some number. It even recomputes to step ranges and does all sorts of fancy things. So to widen our signatures to match things, so remember I did this as an array, often you just want to encompass lots of abstract behaviors. And so you'll see lots of functions that work on all array types or all abstract arrays, and that adds yet another thing. So now you can work on the fancier data types and things like that. So you'll see that as well as you start working with Julia. Hopefully that gets you a good sense of how types work. There's one last thing that I want to talk about here, and that gets a little bit in the weeds about Julia's performance model and how Julia's performance works. And so remember that we use different methods for different implementations, right? And so if I were to add 1 + 2, I get a 3 back. If I were to add 1 + 2.5, I get a floating point number back. And each one of these things is hitting a different method. But you can actually see that it's kind of going through an abstract behavior. If I ask which thing is getting called here, it's going through some abstract promotion mechanism, doing a lot of computation here. And don't necessarily need to specifically state that this is a integer and this is a float 64 for optimal performance, right? Adding 2 numbers darn well better be fast in Julia if we're at all hoping to be a fast language. And so you don't necessarily need to annotate types for performance. In fact, in general, you don't need types for performance. You can do this just as fine without performance. So let's just create a simple function here called compute A and B. And that's going to take 3 times A plus 5 times B. Yeah, let's just do it like that. So 3 times A plus 5 times B. We can compute, 2, 3, that's the integer version of this. We can do 2, 3.5, that's the integer and floating point version of this. The cool thing here is that every time you call this, even though we only have one method, one implementation, each time you call this, Julia will create a different specialization for the types that it happens to get. And so you can see this, and you can kind of see this magic happening just by asking Julia for its intermediate results. You can ask Julia, what code is the computer actually running with what's called code native? This is kind of the native code generation of what happens. Let's turn off debug info. Sorry, debug info none. So by default, it'll print out a bunch of things, line numbers and debug information there. So this is complicated. Here, let me just paste this so that way you all can follow along if you're interested. So I've defined a generic function that doesn't talk about types at all, right? At the end of this lecture, talking so much about types, I've just created a single function with a single method, no overloads, no nothing, that does some math inside of it. And I'm showing you its performance, which is kind of funny. Or I'm actually showing you its implementation, which is even funnier. For those of you who have ever been exposed to assembly code, this is assembly code. This is the actual instructions that your computer does in order to do this computation. And this is kind of how Julia talks to your processor, is it generates this native code on the fly based upon what the arguments are to our function. And so if I have, for example, two integer numbers, 2, 3, it's going to use integer arithmetic to do 2 multiplications and an addition, right? And remember what my compute function was? It was taking 3 times 5 plus 5 times b. That's exactly what's going on here. It's doing a multiplication, and an addition. And these are integer instructions that are extraordinarily efficient. It's exactly, this is the most efficient way to express this to our computer. And you don't need to understand exactly what's going on here. The basics are just that, hey, this is a very specialized method that works for integers. If the second argument is a floating point number, then I need to do a multiplication, and then I convert to a floating point number, and I use wholly different instructions. If they're both floating point numbers, then I use yet more different instructions. And this is kind of the magic of Julia, is that even though I only defined one method, I've now shown you 3 different implementations of that same method, all of which are specialized based upon the types that I've given it. And so these are what's called specializations. And this is what happens when, for example, you pre-compile a package, or you look at the first time that you run a function. So I can ask Julia, hey, let's time what happens when I compute, let's see, what haven't I done yet? Well, I can just do the integers I've already done. It takes 0 seconds. It's so fast that it doesn't even show up here. If I were to do this with, say, complex numbers, right? I've not run this yet. And yet this function will work, and it'll do that computation. It will automatically compile that for me. And I guess this is still too fast for me to even see that compile time happening here. It's such a basic function that you don't even see that compile time. But it is going to compile a special thing. I'd hoped that you would see just like maybe a little bit longer time there, but it's, again, so fast. But it's specialized to work on complex numbers. So this is how we talk about generic behaviors and all the things, and the way that, one of the ways that Julia is fast. Okay, with that, let's take our final break, and then we'll come back here. Maybe if it's okay with you all, let's just do a 5-minute break, because there's lots of fun things to talk about in our last hour. I don't want to take up more time than we need stretching our legs. So if that's okay with everyone, let's shorten this last guy to 5 minutes so we can talk about some of the things that y'all are interested in. Great. See you back here. I guess it'll be about 18 past the hour, wherever you are. Okay, sorry about that. I just had to grab a little bit more coffee. Okay, let's dive back in. There's a few things that we want to talk about that we're, want to discuss. We have a question for making bigger projects and how things compare to object orientation, and how you do work with Julia in an idiomatic way. That's a good one. I have a good notebook for that. I imagine folks probably want to talk a little bit about data frames and just kind of get a little bit of familiarity there. There's also HTTP endpoints and how those work. Anything else folks want to talk about? All right, let's start there. Let's start a little bit about how Julia compares with object orientation and our version of objects, and how that works. So to do that, I'm going to go back to my notebook, and now we're kind of in these advanced topics, right? We've kind of covered the basics of our introduction course, and the remainder of this course is on advanced concepts. The one that I think will be most helpful here, yeah, let's do the one hot vector. So that's notebook 15. We're going to jump ahead because we've kind of covered the basics, and now we're at the point where we can talk about some advanced techniques. And the one hot vector will be helpful in thinking about how we structure code, how we structure our own types, develop our own types, our own classes, as they're called in other languages. This will be a helpful one to get that going. So in Julia, some of you have already noticed that we don't use, the kind of dot function method calls, right? So if you have an array, A is, a random array of 10 elements, right? A random vector of 10 elements. You don't ask for its length by, going into its length, right? You're trying to do this kind of dot call kind of thing. That's not how Julia works. Instead, we know that we take length of A, and now we can actually see a little bit more detail about how length works, right? You can actually ask what method of length gets called. You can ask Julia, what are all the methods for length? There's actually 197 of them. And you can see which one gets called with an array. It is a length where A is an array, right? That makes sense. So that's kind of the basic structure of things. We don't encapsulate our behaviors inside of classes. Instead, we teach Julia, what to do with objects when they encounter a certain verb. And you can kind of think of functions as verbs, right? They're the things that do things, and the objects themselves are the nouns. And so you kind of have this noun verb kind of thing going on. So if you want to introduce your own types, it's kind of like introducing your own nouns, right? You're kind of saying, I want to define something, and you want to just define how it, what it's composed of, or what makes it a thing. And in Julia, we do that by declaring structs, or you can think of it as declaring the structure of a type. And you can do that very, very simply, just with the struct keyword. And this is a special syntax that we've not seen yet. That's why I like covering it in the second day today here, is because this is a basic Julia syntax that you'll see. And if you want to define your own types, or define your own workflows, define your own classes, define your own objects, this is how you define your own objects. Now I'm going to change this just slightly to kind of incrementally talk about how this works and how this goes. I think it's a little bit more helpful to just look at it a little bit more incrementally. So as it's written in your notebook that you have in notebook 15, it has this fancy subtype declaration, and it's saying that it's of a certain subtype. Let's get rid of that for right now, and just create a structure. So I've commented that out. So that's kind of, can kind of ignore that. This is the basics of our struct. And it just has two fields, or two properties to it. There's an index and a length. So we can define that, and you don't necessarily need to know what this thing is going to do. It just has an index and a length. I can create it by default. When you define a structure in Julia, Julia creates the constructors for it. So how you construct it, I can say 3, 4 like that. That'll give me spit back exactly like what I printed it. I've not taught Julia much about my one hot struct yet. I've not told it much about what this does or what it's doing. But this is, the way that you can define this. And I have now defined an object, but there's not much that I can do with this, right? I can't do the things, ask much about it because I've not taught Julia anything about it. So remember, like, with an array, I can ask for a length, but I've not taught Julia how to do the length of my one hot struct. And so I could define this and make it mean something. The reason for being of this example, the kind of motivation here, is that in machine learning, a very, very common technique, a very, very common encoding technique is called one-hot encoding, where if you have lots of classes and you want to describe which class, say you want to say that the second class is true out of 5 classes, you would encode that in a one-hot vector that says, the second index is true out of 5 indexes. And this would be kind of how you would encode to say, like, for example, the second one is the case that you're interested in. And this is a common technique. You don't necessarily need to know the machine learning application to kind of understand that, hey, if you have a lot of things where, all the elements are 0 except for one index, there's going to be a more efficient representation for this, right? By default, Julia, if I create an array like this, it's going to create a space in memory for 5 elements, 4 of which are going to be 0, 1 of which is going to be 1. They're not going to be any other value, right? They're not going to ever be anything beyond that. And so that's what this one-hot struct does. It's essentially telling me, there's a field that says, which index is hot, that is, a value of 1, and the total length. So this means, all the other values are going to be 0. So in just with just 2 properties, I can describe a one-hot vector. And I could potentially describe a very large one-hot vector, right? I could potentially describe one that has 10 values or 9 values, I guess, or potentially hundreds of values just by saying, okay, one hot struct where the second one is true and there are 9 total indices. That is a perfectly valid representation of this thing. I just need to teach Julia that it's going to behave like an array, right? And so I could say, well, what happens when I call length of this guy? What should that be? Well, length of one hot struct, this is my struct. I'll use a lowercase s for what my struct is. And I can just say s.length. And oops, I need to extend. So this is one of the tricky things about this, is that I don't want to define a new function length. I want to add behavior to a function that base is already using. And so this error is saying, hey, if you want to add behaviors to kind of one of the built-in functions, you need to explicitly say, let's explicitly import it. Let's explicitly say we're going to change or add a method to an already existing built-in function, a function that is part of Julia's base library. That's the term that we use for kind of what gets bundled in. So we can teach Julia, hey, this one hot struct has a length, and you can say, okay, so what is length of our one hot struct where the second index is hot and there's a length of 9? Well, of course, that's just going to be 9. Pretty simple, right? But there's a whole host of other things that I want to have happen with a vector. I want it to, support indexing, right? I want to be able to index into this to get the first index out of this guy. But again, if I try to do that, well, I get yet another no method matching. And you can kind of understand, we're using square brackets here to index into whatever this one hot struct is. Well, I just need to teach Julia how to do that indexing. And this square bracket syntax is, under the hood, just represented by the plain ASCII get index. And so I could define this. I could go on and define all sorts of things. But this is where, subtypes and supertypes become really, really helpful, and where we want to go back to the initial structure of our notebook. So I'm going to change this back to a one hot vector and add this subtype definition. So I'm going to say, hey, this one hot vector is going to be a subtype. This is how I get those kinds of type relationships that we had seen from the previous lecture. And I'm going to say it's going to be a type of abstract vector. It is going to be an abstract vector, and its elements are always going to be integers, right? They're always going to be 0 or 1. And so this is how I can say that our one hot vector is of type abstract vector, and it's going to have a parameter of int. And this is that same subtype relationship that we talked about when we introduced wildcards. It's the same idea, same concept, just now we're using it to define a new type. So we can redefine this or define a new type where I'm going to call it one hot vector instead of one hot struct, because now I'm going to say that it's going to be a subtype of my abstract vector. Now if I try to create this guy, so it's not a one hot struct anymore, it's a one hot vector, 2, 9, say. Now I get an error when I try to construct it, which is kind of interesting. And it's actually not erroring when I create it, it's erroring when it's trying to show the value here, because we've taught Julia to expect that this is going to be a vector. And so it can apply to all the methods in Julia that are of type abstract vector. There's multiple dispatch definitions that have applied, that we've kind of realized that, hey, this can apply to any implementation of a vector, whether it's a range, whether it's an array, a sparse array, or any fancy sort of thing, doesn't matter. And so this is how you can think about this, right? But we've not taught Julia anything else. And in particular, we've not taught Julia what its size is. That's kind of a core thing about being an array, right? And the other core thing about being an array is how to index into it. So we need to define those two things. So we can do that, right? And the size, remember, if I ask for the size of a vector, it's going to give me a tuple, because this could potentially be many elements long, right? If it's a matrix, it's going to have the number of rows, the number of columns. If it's a three-dimensional array, there'll be 3 values for its size. Number of rows, number of columns, and then the number of pages of those matrices, as you can think of it, in that third dimension. So we want our size to return a tuple, and even if it's just a vector, it's just going to be a 1 tuple. And so this is how you can write a tuple with just one element. It has a comma there just to kind of disambiguate it from using parentheses to group math expressions, right? So we can do that, and we can define this. Again, remember how I extending behaviors here. Now I'm saying, hey, we want the size to extend the built-in understanding of what a size is, right? And here you can see it's defined for all abstract arrays, right? All abstract arrays should know about their size. You need to, if you're going to be an array, you need to know what your size is. And so we need to teach Julia how to do that. So we can do that definition. That's very simply, using this dot access to grab that property. And that's what dot access does, is it kind of reaches in and grabs properties out of our types. It also reaches in and grabs functions and names out of modules. That's the other use of it, which we've seen. And then the second thing we need to do here is define our indexing, right? And we can just ask, hey, is the integer that we pass in, is that equal to the index that's hot? And this will return a Boolean statement, right? It'll either return true or false. We want to return an int out of this. So either 0 or 1. 0 if it's not equal to the index that's hot. 1 if it is equal to that index that's hot. So this is a kind of cute little way of defining that. So we can define this. Now what happens? So we've taught Julia how to understand this one hot vector's size. We've taught Julia how to index into this thing. And suddenly it prints out just like all our other vectors do, right? Suddenly this thing has all sorts of fancy things built into it, including printing. I never told Julia how to print this thing, but Julia knows how to print general vector types, right? It knows to go in and just ask what the first element is, what the second element is, what the third element is. And let's just store this guy as V so I can play with it a little bit more. So I have this vector that's one hot. And of course I can index into it with V of 1 here. That gives me this guy. And I can ask, which function is actually getting called when I do that? And it's the one that I defined in my script. It's this very function here is what gets called when I index into my one hot vector. Now, what's really cool here is that my one hot vector can potentially be exceedingly large, right? And it's only going to store 2 elements, but Julia will play with it and generate the elements on demand and even, pretend like there's 900,000 or 9 million or however many zeros I put there, elements in my array, with the second one hot, all the others being 0. And it does this very, very efficiently and easily and quickly. And even better is, so I have this 9 element one hot vector that I've been playing with. I can do all the fancy kinds of things that you're used to with vectors, right? So I can do, raise them all to a power. That's not very interesting because zeros and ones to a power are going to be exactly the same. I can add, some value to all of them. So now I get 3s or 4s. And you can see that I'm no longer returning a one hot vector because the one hot vector can't represent, a vector of 3s and 4s. And so I instead just iterate through, work my way through the vector and add 0 plus 3, 1 plus 3, 0 plus 3, 0 plus 3, and so on and so forth. You can even support fancy, mathematics here, right? So if you have a matrix, M is, say a random matrix, 0 through 9, that has 9 by 9 elements. You can take this guy and do a matrix vector multiplication, and it'll select out the second column of our matrix because it's doing a 0 times the first column, a 1 times the second column, a 0 times the third column, and so on and so forth, and adding them all together. And that's how matrix vector multiplications work. And so, of course, when you're multiplying by zeros, it's going to do this. And we have these generic behaviors. I never taught Julia how to multiply a one hot vector with this matrix type, but Julia knows how to do that given just an array that it can index into. And so this is kind of a very, very cool thing. And you can kind of see which function gets called here. So you have this star, and it's defined on abstract array with 2 dimensions. That is an abstract matrix. So A can be any matrix type. And X here, the second argument, is 1-dimensional, so any vector type. And it knows how to do this multiplication for us. And that's pretty cool. So we can even go farther and define more methods. For example, there's no reason that Julia should have to multiply all these zeros and ones. I know that a matrix times a vector is just going to give me the second row or whatever, or I'm sorry, whatever column is the hot column. If the sizes are compatible, and so I can do that optimization. And that's how multiple dispatch allows me to implement all sorts of fun optimizations. And the best optimizations are work that you never have to do, right? And so I know based on the structure of my one hot vector here that I can implement star for an abstract matrix, say A is an abstract matrix, X is my one hot vector. I know that instead of doing the generic matrix vector multiplication, I can just index into my matrix with the index that's hot. And that's, that's the column that I want to grab, and I want to grab all the rows of that column. And that's how you can do this. You'd want to be a little bit more careful here about how you check bounds and make sure that the things are safe and you know, that the shapes are compatible. But this is the way that you can use multiple dispatch to your advantage. And here we're saying, hey, when we know that this is a one hot vector and this is a matrix, we can do something fancy. Just like before, though, you have to do this a little bit trickily, because if I do this, it'll say that it needs to be explicitly imported, right? So I have to, again, just do base dot star. And then because star is a character in Julia that has special parsing around it, I have to do something really annoying, like put a colon there or something, and then that works. And then we'll get the same definition, but with much, much better, we get the same answer here, but with much better performance, because instead of doing we're no longer doing any multiplication at all, we're just taking a slice of our matrix, because that's what the definition is here. We know that from the maths. So that is kind of the basics of building your structure. The reason that I like this example is because it talks, we've defined a structure, and in traditional object orientation, you would call this a class, right? And what you would do with your class is you would bury your methods inside here, right? So in other languages, not Julia, don't do this in Julia, you would define size in here, right? Equals something. And then you would call it by like your v.size or something like this. We don't do that in Julia. This is not what happens. In Julia, we very, very cleanly separate out your structure or your object, your noun definition, and your behaviors. And so by doing that, it kind of becomes a lot more linguistic, right? Why should a vector be in charge of multiplication, right? Why should it have to encapsulate multiplication? Or perhaps an even better example is addition. Why should one left-hand side or the right-hand side be more privileged, or you have to do reverse dispatch or all sorts of crazy things to figure out which one's prioritized? The simpler answer is to simply say, hey, let's define generic behaviors and then teach the specific behaviors we need and build up everything based on those generic behaviors. So that's kind of the basics of object-oriented design. In Julia, you can use object-oriented design, but you just kind of have to think about it a little bit differently, because you're separating behavior and structure a little bit more cleanly than what object-oriented traditionally has done. Hopefully that's a little bit helpful comparison there for how we compare and contrast with object-oriented languages. You can totally do object orientation here, right? You have a vector object that has behaviors. You just don't encapsulate its behaviors inside the class definition itself. You only talk about its structure definition. With namespaces then, generally what you'd want to do is you'd want to encapsulate this into a module. And so you can define that very simply with a module keyword, and kind of the traditional way of doing this is to say the module is the plural and they export the singular. So a module of one hot vectors, for example, would define a one hot vector. And this is just a simple way of encapsulating all your behaviors in one simple thing here that allows you to then eventually move towards creating your own package, wrapping things up, and building a much larger ecosystem out of it. And one of the things in the packages notebook that I kind of skipped over was how you can define your own packages and build your own packages. I'll point you to in Julia Hub, there's a PKG templates package itself. It's kind of a meta package that helps you create packages with the correct structure that kind of uses the best-in-class tooling, gets you set up to generate documentation, gets you set up to run continuous integration, so you can have tests, sets you up with tests, kind of does the best practices for you. So you can jump out here, take a look at the documentation, and learn a little bit about how this works. The user guide tells you how to go about doing it, and you can dig in there, lots of depth as you play around with it. But I encourage you to see how that works. Okay, any other questions about kind of code structure, building your own types, things like that. If not, let's move on to data, right? Data is king. That's what all these things they talk about and how they work. So to talk about data and data frames, let's see, let's go to, oh man, I thought we had a nice example here for data frames. I need to commit that, I'm sorry. Let's see, is it in here? That's not it. Okay, we'll just create a new notebook here for data. I can do that. Let's just do, so up here, I'll go to my file editor. I'm just going to create a new notebook. We'll call it 22 data frames. So we want to bring in data frames, right? We've already added it to our environment. We can just say using data frames like this. That will bring it into our environment. I want to also add a simple package here. Let's see. Yeah, let's do that. Add our data sets. So one of the cool things with the PKG mode here is that you can tab complete our data sets. So I just hit our data. I knew I wanted a bunch of data sets, and there's several of these things. There's a classical bunch of data sets that are already bundled up for you from the R programming language, and we've just cribbed off of their work and exposed that to you all in the R datasets package. So you can add that guy in to your environment. And then we'll say, okay, so we're using data frames using our datasets. Is it capital or lowercase? I think it's lowercase. Oops. There we go. Let's shrink this. So let's just hop over while that's compiling. We'll jump over to Julia Hub and find our data sets and learn a little bit about how this works so we can see how we load this in. We can jump to the documentation. And there's a bunch of data sets available to you. Kind of one of the classic ones is this IRIS data set. And I'll load that one up just because that's one that folks tend to be a little bit more familiar with. If you're not familiar with it, it's just fine. So I just hopped over to the documentation here and copied this first line of code. And I'll go back to my notebook here and execute that. So this will, by default, load in this data set that has a bunch of details about it. And if I expand this out and just type in IRIS here, you can see that it prints out as a data set. It's actually printed as a table. And tables are kind of like matrices, right? I have this data frame. It prints out, it says what its type is. It says it's 150 by 5. That's kind of, it seems suggestive of a size, and you can actually ask what its size is, and sure enough, it supports kind of the same infrastructure as matrices do in some ways. It kind of acts a little bit like a matrix, and in fact, I can index into it kind of like a matrix. So I can get this first element out of it here, the sepal length of the first row, just by indexing 1, 1. And that gives me what I want. There's a few fancy things here beyond just being like a matrix, though, in that, I have names here. So each row is an observation of a particular species, a particular plant from a particular species of iris with, some details about its petals and sepals. And they're in different orders here. And you can see there's actually 3 different species. And kind of the way that you work with data frames in general is, you can look into them. You can actually identify them by their, sepal width. You can dig into them with this dot access like we had seen before. And that'll just give me the vector of all the sepal widths. And, you can look at the vector of all the species, for example, capital. And you can see that this is a string, and there's, so some of the fancy things here beyond being a matrix is that it supports a heterogeneous mix of types. You know, we have some floating point numbers, some strings, and they're implemented efficiently. It's kind of like a collection of vectors. And I can, of course, index into these things. I can use all the great data handling tools that Julia exposes. So for example, I can look at, how many unique species are there? And I can just ask, what are the unique species out of our iris data set? And there are 3 different species listed here. So then the kind of traditional way of working with data here is to do a technique called split, apply, and combine. So what you want to do is, like, essentially you want to group your data, do some kind of transform on it, and then combine it back together to see what the final result was. So in data frames, this is done very, very simply and easily. You can just kind of ask to, group by your iris data set by, for example, the species. And by doing that, you end up with 3 different groups of your data frames. So you can see this first group has 50 examples where the species is Setosa. There's a second group, and then the last group is, again, 50 rows of this last, the last species type. Now, what's really cool here is that you can then combine these groups back together by applying some function. And so I have these groups, I can call this my groups, or like this. So I can combine my groups back together where I want, say, the sepal length to be the averages. Or let's actually start with the max. Oops. Where did I do wrong here? Yeah. Oh, right. I'm passing in the wrong thing. There we go. So let's do. Yeah. Okay. There we go. Sorry about that. At the end of the day, I always get a little bit sloppy in my incremental writing here. So let's pull these things up into my my editor, so that way you all can follow along a little bit easier. So what I did here was I defined my groups, right? I split apart my iris data set into 3 groups based upon their species, right? And now I have this set of groups. I want to combine them back together, applying some transform to a given given column name. So for example, I can go in here and look at what the maximum sepal length is when divided amongst my 3 species. And it automatically goes in and computes these things. It even names my column automatically. I could change this name of my column just by saying max sepal and do it like that. That'll give me the capability of naming these things separately. There's something special that's going on here that I've not talked too much about, and that's that I'm naming my my columns with these colons, and this is a use of colon that we've not seen yet. And by using the colon like this, it's actually just creating what's called a symbol. It's a kind of a short string representation. I think actually data frames has now converged on the fact that it's just as easy to sometimes use strings. And so I think they allow strings here too. Let's see. Yeah, so you can use strings or symbols there. Perhaps it might be a little bit easier to just use strings because then you don't need to talk about a new data type that we've not really talked about much. I think that'll work too. Yep, sure enough. So you just pass in the name of the column here, and that then the transform that you want to do to each subset, right? And so here I'm asking for the maximum. I can also do, a whole host of other transforms simultaneously, right? So I could also add in here, say the mean sepal, right? So mean sepal, and I want to pass in mean here to do that. Well, if I do that, I end up with an error because mean is not defined. Mean has been relegated to a standard library. I just need to bring in the statistics standard library, and then that will work just fine. So again, we'll just bring that up into my using statement up here, just combine all of these things together. And now that'll work just fine as a single standalone script. So this is how you can kind of do this. Of course, there's a lot of depth here in terms of what you want to do. You can also group, use these groups to plot things, right? You can plot all of these things. So let's also pull in plots here. And actually, let's add one more package called stats. I can never remember whether it's plural or singular. I want stat plots. So I'm going to add yet one more package that I forgot about during our package side of things called stat plots that allows you to do some very simple and easy plotting mechanisms. Oh no, I'm going to be in trouble here though, because I think I'm going to need to recompile some things. Yep. This may or may not work. We'll see. The idea here is stat plots kind of adds in a bunch of extra capabilities to the plotting environment and some nice grouped plotting recipes by default that you can work with. So you can jump over to, again, Julia Hub is where you can find these things. Stat plots. Go to the documentation. And you'll see all of these guys. Oh, I think I wanted the plural version. Are they the same? Yeah, they're the same. I think they're aliases of one of each other. Oh, that's confusing. Yeah, they're aliases of each other. That's very confusing. We should have fixed that up, clean that up. Because yeah, if you click on stat plots, you get redirected to stats plots. Goodness, that's a mess. That's frustrating. That's why this didn't work. I'm going to rm stat plots and add stats plots. Oops, that's not going to work. But that gives you an idea of how to go. I know I'm not going to have time to dig into this very closely, but using, but hopefully I'll be able to do that shortly to show you how that works. Let's see, there were a few other questions. One that I think would be fun to go over here just briefly. Oh, here we're in. Let's see if I can do this quickly. So the cool thing here is, you can do grouped plots really nicely where you color things based on, what the color is. And it adds this special macro @df that that allows you to, support colors and things like that. So let's see here. Let's see if I can do this quickly. So we can use this @df, and essentially what it says is, within the iris object, we're going to plot, let's say, the sepal length by the sepal width. And we'll color it based upon the species. I think this should work. Oh yeah, I've already used stats plots. Let's do that. Ah, shucks, I'm in a weird state now because I've loaded both of these things and done some funny things. Oh, I'm using the, let's see here. I used the wrong. Yeah, I'm not sure. Sorry about that. It's late in the day. I'm not fully with it to do these off the cuff examples, but hopefully you get the idea. This is possible to do some very nice grouped plots with colors and things like that. So this, hopefully we can fix this, and I'll add this as an example to the repository later on as I go updating this. We'll keep these materials accessible to you all. So with that, I know we're getting very close to the end. We're almost out. The last thing that I want to point you all to are some resources that you can all go to as you continue your Julia career. Hopefully this has put nice grounding for you all about how Julia syntax works, the basics of the library. Everything up and beyond that is going to be based upon what packages you are using, and the syntax is there, but hopefully most of these syntaxes should be fairly straightforward. The only thing that we didn't really get to, and my apologies for this, is macros, these special macro things, and all they are here is a way of kind of shorthand writing things. So it essentially transforms the code you wrote to something fancier. And you can kind of think of them as pseudo keywords, and everything that follows a macro, that is everything that follows that fancy @ sigil, is going to do something a little bit different with what you get. Okay, there are a few other questions here that I'm happy to answer. Oh, I want to point you to resources. That's what I was going to do. So at julialang.org is kind of the main website for Julia. We sent you here to download Julia beyond just downloading Julia. There's a really nice tab here for the community. We try to be a very welcoming and encouraging community, and there are lots of official channels that you can connect with us on. GitHub, you've seen, we use that for almost all code development in the open source ecosystem. The Discourse messaging forum is a really great place for connecting with other Julians and getting up to speed. It's a nice place to ask questions from beginner to advanced. Lots of helpful folks there, as well as chat on both Slack and Zulip, are kind of like these instant messenger kind of apps that a lot of us are using. So I hope to see you on one of these boards. Even if you don't join these boards, you can also go to the documentation. This is kind of the technical manual for Julia itself. There's a lot of really, really awesome information here, from the very basics at the beginning to some of my favorite chapters here are at the end, where at the very, very, very end here, there are these handful of things that aren't really, they're kind of out of sequence, and I think we should move them around a little bit. But things like frequently asked questions, a style guide, some workflow tips, some performance tips. I recommend, it's kind of funny. I often recommend folks who've now mastered the basics of the language to jump to the very, very end of the Julia manual after getting the basics down. One of the most helpful pages here is actually the noteworthy differences from other languages. So if you're coming from another language, say Python, I know some of you are, you can kind of get a little bit of a leg up and compare and contrast about how Julia works as compared to Python. And can kind of help shortcut away from some common pitfalls that other Python programmers have found. These noteworthy differences are largely updated and created by recent adopters who come and see, oh, this is a little different. I got caught off guard by this, and they'll add that as a bullet point here. So it's a nice spot to start. I know we're beyond the set time here. I'm happy to stick around and answer. I think there are 3 outstanding questions, and I think we can cover some of them fairly quickly and in fairly short order. The HTTP APIs, the traits and light graphs. And I'm happy to talk about those if folks are happy sticking around a little bit. And yeah, a reminder for folks, thanks Clay for reminding me that we do continue this sequence of courses. Next week, we're talking about machine learning. The week after, we're talking about high performance computing or parallel computing. And so we run these triad of courses somewhat sporadically. We're not sure how much we'll continue doing this. I think we'll probably do it again. My guess is we won't do it until the new year, given holidays and whatnot. We tend to run them about every other month or so. And so, yeah, it should be fun next week too, for those of you who are joining us on machine learning. And I'm happy to stick around for those of you who want to stick around. You're totally free to go, but if you want to stick around to learn a little bit about HTTP APIs and traits are kind of an advanced dispatch technique. And we'll poke in at light graphs. I'm not a graphs expert myself, but we can take a look at the package and kind of see what it provides and how it works. Yeah, you're welcome to contact me. My email address is mbauman at Julia Computing. You can find me all over the place. Perhaps even better than email is on Slack or Discourse. I tend to follow those more actively. Email can sometimes get left in the lurch between all the notifications that come at me. But yeah, feel free to contact me with any other questions or join us on those boards. Thanks, everyone. So let's dive into a few of those advanced topics. The one on HTTP is actually fairly simple, and I just wrote a Stack Overflow question. So Stack Overflow is another place where you can go to get Q&A style answers and help. And this is not something that I've written a documentation for yet or a tutorial on yet, but it's kind of a fun little demo on how to, set up Julia to work with an HTTP endpoint, or how do you just kind of, get things going with, how would you set up an API in general? And so this is a question that was asked just a week ago or two that is fresh in my mind. And I have a simple 6-line of code little demo here that shows you the basics of how you would get started with serving an HTTP site. And the way to go about that, we can just go into VS Code here. Let's create another file. Let's see, what number are we on here? We're on like 23 now. 23 HTTP APIs. So I have a handful of packages. We talked about this HTTP package, which I added because I had seen that question ahead of time. We are going to use the sockets standard library because the basic idea here is that we want to set up Julia to listen to an incoming request, and where that incoming request comes from is on a socket. And so there's a few tools that comes there. And what happens when we do that is we want to respond to a request. And so you have a function here that'll do some computation, for example, that'll respond to a given request. And you can set this up to give you a HTTP response. And essentially, HTTP revolves around a lot of codes and things like that. Y'all are familiar with the 404 error that it responds with if something's not found. The error code that you're probably not familiar with, or I guess it's not an error code anymore, the response code 200 means all is well. So nobody ever sees that one, right? Because if a browser sees a response code 200, it just charges right ahead and displays you the website. So when you set up a computation that you want to link to an API, you want to return a response that'll get sent back to a web browser essentially, or something that's going to consume this API endpoint. And they need to know that, hey, everything went well. So it's a 200 response. And then you have some data, and that could be a string. It could be a JSON object is very common in web programming. And we have JSON packages that can help you format things like that. Or it can be an arbitrary data blob. Anything can come across here. Or it could be an HTTP page. It could be a full featured page that can set this up. So you can define a function that will return some sort of response. And then it's very, very simple to set up an HTTP endpoint with the package that handles these sorts of requests. Essentially, you set up a router that kind of says, hey, we're going to add this. You use what's called a RESTful API. So if a browser or some service asks for something at this test endpoint, we'll run whatever happens in the compute function. And then we can serve this on a given port. And this will start up a server on my local computer. And I can just go to, I can open up a web browser here to localhost at that given port. And I'll get back my hello world, or I should. That did work last week. Why didn't this work? Funny. Oh, I returned a 404. What's going on? Did I not run everything here? Compute. Oh, maybe. Let's call this respond instead. I think I might have a funny thing going on here. Oh, right. I've not defined, that's what it is. I want to go to that particular endpoint, which I set up as /test. And if I'm at that given endpoint, then I get my hello world out here. So you can see that I got hello world at that given endpoint. And this is how you can set up a whole sequence of things. And you can dynamically respond to different requests. You could have your homepage respond to something. You can kind of change around. So this is, I set up a Julia function that will respond if I'm at /test here. And there's a whole sequence of ways of setting up things to do all sorts of fun things. But this is how you set up a server. And it's as simple as 6 lines of code there. So that's kind of cool. I found this a little bit kind of a fun example because it's so short and so succinct, but allows you to kind of dig in and begin building out, what computation are you going to run here and how do you need to do this? So that's how you can do that. The other question that Vish asked, to move on to something else, was on what are called traits. And traits are kind of an advanced dispatch, paradigm, or an idiom, I guess is the best way to describe them, that kind of allows you to do something, choose what to do by asking an object what you should do. So I'm trying to think of a good example or a good demonstration. Guess I might just do a dummy example here. So let's, I'll just use the same page here. So traits. The basic idea is if you have some function do something on X, right? You can choose what to do based upon how X responds. So there's 2 ways of structuring dispatch here, right? You can explicitly say, if X is a number, we, now work with a number. You can also do something with X as a string, and you say, all right, I'll work with a string here, right? So this is kind of like the standard dispatch paradigm, right? And that's what we've learned, and that's what we've seen. There's a fancier structure here that you can play with where you can do something fancy with X, where instead of immediately structuring dispatch on this directly, what you do is you ask for, let's say, you ask, how, let's see here. What's a good example? Let's call this, eat. So we're going to define a generic function that you teach something how to eat, right? And you want to know how to eat. We could specifically say, we could say eat, and if you're a dog, we do something like this. You could say eat if you're a cat. You do something else, right? This is kind of that same structure where we have a verb and a noun, and you can eat. Of course, if you eat and you're a sponge, you're going to do something very different, right? It's kind of almost more like an absorption sort of mechanism. Or if you eat and you're a single cell bacteria or something like that, you're going to do something very different, right? The way that you eat is going to be different. So I could go through the entire animal kingdom and define what it means for each one of these things to eat. The fancier way to do this is with traits. And so you can ask, you can define a general structure here where you ask your objects how they eat, or their eating orifice for X is going to be something, right? And so for you can do for a dog, that's going to be a mouth. Eating orifice for a cat is also going to be a mouth. And in fact, you could set up an entire thing for, all mammals. Your eating orifice is going to be a mouth, right? Or I guess not, let's say mammal. Make this a little bit more accurate, anatomically accurate. So instead of directly defining what you do for all the eating things, you can say, well, if I eat, I can go to a specialized eat mechanism for a particular orifice. Eating orifice. Sorry about the crazy example. And you pass the object itself. And so then you have eat for mouths. You have some definition here, and you chomp, right? If you eat for what do you want to call it? Cellular channels X, then you do something else where you would, absorb or something. And this allows you to kind of generalize a whole class of behaviors that don't just apply to eating, but also apply to, say, vomiting. I'm so sorry about this example. You do one thing with you have a mouth, you do something else. If you have cellular channels, these kinds of options are available to you, and you can play with them that way. And this allows you to describe how these things work based upon a class of behaviors, right? You're asking your type to return some other type that you then dispatch on, and that's what we call traits. The type of structure through which you eat is a trait, and you and I have mouths. Other animals might have other ways of eating, and then you can structure whole classes of dispatch, not just for eating, but for other sorts of things that you do with your mouth. I don't know what those are. Talking, maybe, if that's appropriate for the particular animal. But hopefully that's an okay structure. Concretely, one of the most typical ways of seeing traits in Julia is the fact that there are fast ways of doing things for particular objects. And so one of the common ways of working with traits is you split based upon what's the fastest implementation. And so you can ask, what's the fastest way to work with this object, and then have a fast implementation. So hopefully that's helpful, Vish. Yeah, exactly. It kind of helps you reduce if-else's, kind of helps you classify things into a single trait, right? You define things with traits and things like that. So that's traits. We're at 319. I think I might call it short here. The last request that I didn't quite get to, and I'm sorry, Vish, was light graphs. And of course, on Julia Hub, I think they have really awesome documentation. I've not done much with light graphs. We should add that to our kind of our training here. And really, we should split this training up into, and to add an intermediate training with all these advanced package uses. But I think there's, let's see, do they have tutorials? I think they might have some, yeah, there's some basic examples on working with them. Oh yeah, they have tutorial notebooks, nice. So these are IPython notebooks, and they look like they're a little old, I guess, but hopefully they could help you get through some of those things. Oh, right, PyCall. I'm sorry, Peter. That we actually have a notebook on, and I can go over much more concretely pretty quickly here. Let's do that. So notebook 21 is explicitly on calling Python, and there's some fun examples here. I forgot to add these, so I'll have to add PyCall and Conda to get this going. The one tricky thing with PyCall is that it builds PyCall to connect with your Python implementation or your Python binary. And for a lot of users, that can be a little bit tricky. And so sometimes when it builds PyCall here, this build step is it connecting to Python. And if Python is in a weird state on your computer, it might fail. It's a little bit tricky to get going. The Conda package can kind of help solve some of that and make sure that you're using, it'll actually ask Julia to install Python and install an entire Python package manager, because so many people have broken installs of Python on their computers. We found that this to be a little bit more robust. But what's kind of cool then is once you have this and you're using PyCall, it'll take just a second to compile here, is that you can connect in with Python, and there's a whole host of ways of just kind of, you can actually write Python code in Julia. And one way of doing it is you can actually ask for a Python object with this special string type. So we've not talked about these yet, but these string types with a prefix are kind of like a special way of interpreting strings. And so Python can, instead of defining a string, right, if I just write the string sum, it just prints out sum. If I prefix that with a pi, it's saying, hey, I want to work with the Python object and connect in with that. And we'll ask Python for its to evaluate it, and you evaluate sum in Python, and Python gives you back its sum function. And the cool thing is that you can actually call that in Julia. You can ask Python to call the sum function on a Julia data structure. PyCall will automatically translate that Julia structure into a NumPy or Python structure, like a list, and call that function for you on it. Even cooler, especially in VS Code, is that you can write entire Python functions in Julia directly. And in VS Code, it'll actually use the Python syntax highlighting for you. And that's pretty cool, right? Def is not a Julia keyword. That's not typically not going to highlight like this, and would be a syntax error if I wrote it in pure Julia. But by protecting it in these Py strings, well, I can actually define a Python function that will add one. And so you can call that, oops, I ran all of these functions here. That's going to be annoying. I hit Shift Enter instead of Control Enter again. But so you can add one with this, and it will actually, ask Python to do the addition of one for you. And you can even do all sorts of crazy things like back and forth recursion, where you alternatingly call Julia to Python to back and forth, and there's all sorts of fun things to go with this. Lots of depth here. You can go through this example. There's some more examples on how this works, but it's pretty straightforward to get these things going. There we go. So now we can just run, add one, for example. This is actually running Python code from Julia. It's going to be, if you're doing this, right, you're going to get the performance of Python, but it's really nice to not need to rip out your entire code base. You can just call into it directly and work with it directly like this. You can even use these fancy PyImport statements. Let's see here, where is this? Let's go down to, so you can import NumPy and you end up with NP as a module that kind of works just like it does in Python. You can ask for the range of, do a range of 5, like this is doing the NumPy thing, and you get back a Julia array. Again, it does the conversions at the boundaries for you and tries to do it without copying, in fact, which is pretty cool. And so you can do all sorts of fun things with math. Of course, that's going to be the same as using Julia's sign function. And there's an even more fancy thing that uses the SciPy's optimize function here to optimize a function in Julia that we've defined in Python, that we use in Julia, that we use the optimizer called from Julia. And then there's another example of using the Julia optimization toolkit instead. With the Julia function, you can see the timings of all these things. I'm not going to go through all this, but it's kind of a fun notebook to work your way through if you're familiar with this. So in general, the boundaries here are pretty low latency. The performance, again, it's going to be limited to Python's performance, right? If you're working in Python, you're going to be limited to Python's performance. We try to limit the overhead, and there's actually some advanced functions that you can use that limit the overhead even more, and will, instead of converting to a Julia array, just give you the NumPy array directly. That is a little bit harder to work with in Julia, but works just fine and can reduce overhead a little bit more. They live in the same memory space because it's an embedded interpreter, and so it in general is pretty low latency. This is my favorite way to write Python code, by the way, is within Julia. With that, I think we can bring this session to a close. Thanks for those of you who stuck around late. I know that this is a long day, but happy Friday, and hope you all have a good weekend, and hope to see some of you anyways later next week and the week after, or if not, on Discourse, Slack, or any of our other many community channels. Thanks everyone for being a part of this, and thanks for all your great questions and interaction. This was a lot of fun.
Hey, Matt, can you hear me okay?
Yes, I can.
Hey, it's Mark Wiggins. I just wanted to say thank you so much. I think based on the group chat, it's probably the least experience coming into this, and I feel more confident than ever. And I hope it'll take me some time, but I hope in a couple months you'll be reading about how Julia helped Royal Caribbean Group come back to service.
That's so great. I look forward to it.
Thanks so much.
Thanks
I really
for saying
appreciate
something.
it.
Absolutely.
Yeah.
Thanks very much, Matt.
You bet. It was good seeing you here, Vish, and yeah, hope all goes well.
Cheers. Have a great week.
Bye-bye.
Bye.
You too.